All right, we'll move forward. So we were discussing about max terms. So max terms again. So this is also correlated with the same sort of aspect. In which in min terms we learned about this, right? So remember, in min terms we associated a complemented variable with zero, and yeah, so a short gist till now could be, firstly, we learned about simple number systems, one's complement, two's complement, and stuff. And then we learned about simple digital systems, how to convert between one system to other system. We learned about gray codes, we learned about BCDs, where we convert one number system to another system, right? That is all that first unit matters. Now, second unit is again simpler to understand. All you have to know is basic gates. Basic gates like AND or not, XOR, XNOR, NAND NOR. That's it. Okay. And then min terms and max terms. So what are min terms? Again, duality. So you formed true or false values, right? So trues or a variable can attain either one or zero. And you formed a function with all of these variables combined. You can put any operator sort of thing and make this function work according to you. Now, talking about duality, you will replace in every AND by OR and every OR by AND, every 1 by 0 and 0 by 1. That's it. And min terms, but let's say you have few variables. Let's say you have variables A and B, and you're combining them with an AND operator. Okay, you can combine them in various ways: A B, A bar B, A B bar, A bar B bar, and so on. So these are all standard terms which you can form. Right now, you will interpret the same variable as if it is not complemented. If the actual variable, you will interpret that as a one, and if it's going to be a complemented variable, you will interpret that as a zero. Okay, so if you have just AB, A is interpreted as 1 and B is also interpreted as 1. So technically 1 1 in binary is what? 3. So you'll put small m3, small m meaning min term, 3 meaning it is going to be the term capital AB, right? Similarly, A bar B. A bar is going to be 0, B is going to be 1. So this will be capital M1. A bar B bar. This is going to be 0 0, capital M 0, and so on. You can do that for 3 bits also. 1 1 0. What happens? 1 is actual variable A. B actual variable B. 0 actual variable C bar. But I also understand that these are all min terms which are products. All these are only what combined with AND expressions, right? AND gates. So just understand that these are all standard products. And max terms. Whenever you talk about max terms, the thing which will be involved here is you will have R's. These are all sums, right? And you will interpret every complemented variable as 1, every actual variable as 0. Okay, so here this will be a complemented variable. So technically a bar plus b complemented variable will be 1. This will be 0. So this will be capital M2 and so on, right? This will be what? 1 1 capital M3. This will be what? Small 0. Yeah, sorry. Yeah, capital A would be 0. This is complemented, so 1. So there will be capital M1, right? So simpler to understand. These are all min terms. Hope you are clear with the basics. Is that fine, everyone? Can we move forward? Now, f is equal to a plus b c bar. You want to express this as a sum of minterms and product of maxterm formats. Okay, you can work along this in two ways. One thing is finding the sum of minterms, getting all the remaining terms and put them in the maxterms formula. That's one of the things. Or you can put them in the other way around, finding all the maxterms and then you can find the minterms from there. Okay, but the simplest one, let's just do sum of minterms here. Right, I'll just tell you the approach to do that one, but we'll just do this. So what happens? You have a simple formula. What do you mean by a minterm or max term? It's a minterm is just products. But understand, every minterm will contain all the variables, right? If you're talking about A, it will contain all the variables present in that function. So this term, so a term is separated by an operator. Here you have a plus operator. See that? So it will be, one sec, please. Yeah. So you have a term A plus BC bar, right? So what happens here? Uh, A is a single term, BC bar is a single term, but single term does not contain all the variables. So what do? You want to make it contain all the variables. So you will always do what? A into A dot 1 you will do, right? So you will always do A dot 1 And in that one, you'll add what? B plus B bar. You'll add what? B plus B bar, right? So A into B plus B bar, and you add one more one, that will be C plus C bar, right? So you are introducing all the other terms by using simple identities. B C bar, you can introduce one A plus A bar, right? And you will try to simplify this very simple: A B C, A B C bar, A B bar C, A B bar C bar. And you can do that for other things. You can cancel out all the things which will repeat, and you will interpret all these min terms or min terms as the respective terms, and you will put them under sigma, because sigma is what? Sum of products form, right? So that will be sigma. And all the remaining terms in that bit system, so we have three variables, so all the remaining terms, what are they? 0, 1 and 3, right? You will put them under pi, which means product of sums, meaning it's product of min terms, right? Min terms is sum. So this will be your sum of products form, and the product of sums form, right? What if you want to do the other way around? If you want to do the other way around, so you have A plus BC bar, you want to make product of sums, and using that you want to make sum of products. Use a simple distributive law. What is that? A plus BC bar is nothing but A plus B into A plus C bar. Very simple. Now you don't you have C term here, you don't have B term here. So what do? You want to do something to introduce that. How can you introduce that? I can just put plus 0. Because there was a dot there, I put dot 1. Because there's a plus here, I have to put plus 0. And because there's a 0 here, what is the identity I can use? I can use CC bar. Because CC bar is 0. Similarly, A plus C bar, A plus C bar plus BB bar, right? So what happens? A plus B plus C, A plus B plus C bar, A plus B plus C bar, and A plus B bar plus C bar. Simpler one, simpler to understand. You will get all the terms. You will interpret every max term as a as a corresponding what? Sum, and you will put them under pi. All the remaining terms will come under what? Your sum of products. Till that everyone's clear. Any problem till now? Just brushing up whatever we did till now. We just learned whatever Boolean algebra corresponds to. All the variables will be there. Each variable can take either of the values true or false. We combine them in or and AND expressions to obtain product and sums. Whenever we had a sum, it will be a max term containing all the variables, and you will interpret every not a variable as what? 1, and every actual variable as 0. And it's the other way around for a min term, right? And min term is a product. We associated every min term with a corresponding designation. Now, and we also put an expression. It was expressed in terms of what? A min term and a max term. Okay. Now, how do you feed them? How do you make the circuit? Guys, this is very much simpler. I'm not emphasizing more on this because circuit logic should be clear. Because A B bar, C D bar E, A C bar E bar. So what happens? Just put respective lines of input. Okay. What I'll do is I'll just, so this is not a standard method of doing this. They've just explained you in this manner. You will put standard lines. So A B C D E, right? You will put gates, right? B bar is needed, D bar is needed, and E bar is needed, right? I'll put that A and B bar should be combined. So I'll put A bar and B bar. I'll combine them using an AND gate, right? Similarly, I'll combine C, D, and E line, right? And that is there. So you have to name them, okay? Right? B bar line is here. So this will be B bar. Now, moving forward, okay. Moving forward, you will combine them and you will combine all of it. So all the expressions which you got. So AC, let's assume only these two are there. You'll combine them using an OR gate. You will get the final expression. Simpler one. Product of sum format is where you have all of them as what? All the sums are going to be multiplied only. All the sums are multiplied. Is this a sum? Yes. Sum? Yes. Sum is multiplied. Sure. Is this a sum? Yes. Is this a sum? Yes. An individual term is a sum. Okay. An individual term is a sum. We are not talking about min terms and max terms. Min terms and max terms are elementary sums and elementary products, which have all the terms in that. All the terms in that. All the terms are in when you're using a function, all the terms of that function should be there in every single term. Right? That's what we did last time, right? Now this is a simple sum. So right, simple sum. So elementary sum. So this is a sum, this is a sum, this is a sum. Right? So this is a very simple product of sums format. This is a sum. This is a sum. You are multiplying it. But this is what? This is what? This is not a product. So this cannot be regarded as a product of sum, right? You have a product here, you have a sum here. This is not a collective product of sum expression. So that's not there, right? So you can always put product of sum formats will be what? OR gets ANDed. All the OR gets will be ANDed together. Now, how do you simplify Boolean equations? Firstly, what is the objective to simplify Boolean equations? You need not, you firstly, you cannot put a lot of hell lot of what cost and energy into manufacturing chips with a lot of terms. So basically, you have to literally, so imagine they give you some 16 terms, okay, and they ask you to build it using a simple logical circuit, right? Simple circuit board which we have in a lab, okay. Will you be fine doing that? Okay, putting hell lot of wires, putting hell lot of gates, putting hell lot of signals, putting hell lot of input and output lines, right? Will you do that? Or will you just simply construct just four input lines, giving a simple expression like that? Okay, so simplification of Boolean expressions give that particular thing, right? When I have a big lengthy expression, I can just simplify it into parts and I can do that myself, right? So that is simpler, even more simpler. So that is there. And then, what do you mean by canonical and standard forms? And what is this? Canonical form. So, understand, standard form is the one which we have in the most simplified manner. Standard form is the simplified manner. By the term simplified, I mean minimum number of literals, minimum number of terms, or minimum number of variables in your terms, right? In your expression. So that is what we mean. Canonical forms are just what the sum of product of sums format which we expressed here, sum of minterms and product of max terms. That is the canonical form. So you see here, canonical SOP form is just something of this sort, which will contain minterms put together, which is a sigma of 1 4 5 6 7 and so on. And this is canonical POS. And understand, both are dual of each other, right? So that is there. And standard is just a reduced form. Reduced form. You'll reduce this, right? How do you reduce this? You might use Boolean loss. You might use K-maps. You might use Coin-McCluskey method. Okay. Now all these three things are there, but Boolean loss, you don't have. You don't. So canonical forms. Talking about canonical forms, canonical is just something where. One second, please. So, talking about canonical forms are just your same expressions, which is in the sum of minterms or product of maxims format. That's it. Very simple form, straightforward. Okay, you had a reduced expression, but what are you reducing it from? You're reducing it from an expression which contains a lot of terms, right? So those terms, those expressions are called as canonical forms. This is a simple canonical SOP form because you have a lot of products added together, so sum of products, and you have what a lot of terms involved, right? This is not a standard form because it does not reduce it to less number of literals. So that is the thing, right? So canonical is that. Now, why do you move from naive approach to other methods? What is the naive approach? Again, a naive approach deals with just what comes with your instincts, what comes with your own ideas, right? So will you be able to just say, oh, okay, I can proceed with this step, okay, this is nice, but can I do this? And you might end up with another step which might not be feasible, right? I mean, there are always feasible steps, but there is no other standard way to deduce an expression in a naive approach. That's why you have came up method, right? And coin McCluskey is also there, which is not part of use, right? So let's talk about this. Let's talk about a naive approach first. Simple Boolean laws. So we till this point we learned about various Boolean laws, right? So an XOR we learned, right? I, something like these are just brush up concepts for you to understand while applying Boolean laws, right? So A XOR B is just A bar B plus A B bar. A X nor B, just you put this A bar B bar plus A B. You can derive this using simple Boolean simplification. You see here A plus B the whole bar, A bar B plus A B bar the whole bar. You can just apply De Morgan successively. You can multiply terms, you can multiply terms successively. Whenever you have A bar, B, you'll put 0 and you will end up with this, right? And simply, you can also reduce this A bar B bar C plus A bar B C bar plus A B bar C bar plus A B C. What do you do? You can take, so this is one of the things, but XOR gate again is it's good enough, it's complex enough that you don't want to reduce it to that format, but it's good to realize it. In a circuit, it's good to realize it. But if you're asked to like put it in a standard reduced format, try deducing if you can make it to less number of literals than an XOR gate. Okay, so that is all, that is always there, right? So yeah, so see here, we have this following expression. We want to reduce them using simple Boolean laws. I'll just do one thing maybe. I'll maybe do this first one. So A bar BC plus A B bar C plus A B bar A B C bar plus A B C. Okay. So what happens? I try to see variables where I can use my Boolean laws. Okay. I try to see wherever it is common and I use this. Where is it common? I see A B is common. Very simply, I see A B is common here. So C plus C bar will just become one, right? And then I can just write the remaining here. Again, I see what? I see A common here. I see A common here. I'll take A common. So what happens here? B bar C plus B, right? What is B bar C plus B? It will be just B plus C, right? B plus B bar C would be just B plus C. So this will just become what? A into B plus C. And this term just is as it is, A bar B C, right? So let's try to write this down. A B C, A C, and A bar B C, right? Now what happens here? Again, again, you can take B common. If you take B common, if it's going to be A will be there. So what will be there? A plus A bar B, right? Take B common, A plus A bar B plus AC. Again, A plus A bar B is nothing but A plus B, right? So it will be just AB plus BC plus AC. So that is your reduced format. You cannot reduce it further, right? I mean, all you can do is just take one of the variables common and so on, right? But yeah, this is the reduced format. And understand this is actually an expression which you'll use in the future also. This is a carry output of a full adder. Okay, just understand that. You'll have one bar at a time. A bar BC plus AB bar C plus ABC, ABC bar ABC, right? So that is it. So a NAND gate is just and with not it, or with not is nor, and exclusive OR gives you one if in the cases where the bits are different, and it gives you zero in the cases where it's same. And XNOR is the reverse of it. Okay, understand this also. Whenever you supply 0 to an XOR gate, what is that supposed to give? See, whenever you have these doubts, no, just plug it in and check. Always. Digital design helps in that case. Plug it in. 0 XOR 0, 1 XOR 0. 0 XOR 0, same, 0. 1 XOR 0, different, 1. So technically, whatever you are supplying here, irrespective of whatever you are supplying here, you are getting that same thing. 0 0, 1 1, right? So A XOR A would be just A. Now let's do it with 1. 0 XOR 1, 1 XOR 1, right? 1 is standard here. We're just putting 0 and 1 in these spaces. 0 XOR 1 will be 1. 1 XOR 1 will be 0. So you observe it, right? Because it's different 1, same 0. But I've observed it, right? Whenever you supply it, the complementary output is reached in the other side. So whenever you want to complement an output, what do? You just XOR it with 1. That will give you the one's complement of it, right? And when you complement with the same thing, obviously 0. When you complement with the complemented thing, right? Inverse things, right? A XOR A bar, that will give you what? 1, because different. So that is also there. It's commutative, associative, distributive, all that is fine. Okay. Now, implementing logic gates using universal gates. I don't know if you were taught this elaborately. Okay, I'm just where you taught this implementation of logic gates using universal gates. Did you try actually building the circuits for implementation, or just this concept? Can you please confirm quickly, please, in chat? You try it practically. Okay. Okay, I'll just give you the glimpse of it. I'll just maybe I'll give you a glimpse for NAND. You can do for NOR. Okay. So what happens here? You want to build. So basically, NAND and NOR are called universal gates, right? You can implement all the other gates using NAND gates, NAND and NOR gates, right? So individually, with just NAND, you can implement everything. With just NOR, you can implement everything. So what happens here? So let's try to build this, right? So how do you make all the gates using NAND gate? All the gates using NAND gate. So understand this. Understand this. So you want to implement, let's say, an OR gate. Okay, firstly we'll just do what NAND gate. How do you implement a NAND gate using NAND gate? Just NAND gate. So let's just take it two input lines. Use a NAND gate. It'll give you a NAND gate output. That's it. Done. Very simple. NAND gate. You're just using NAND gate there. Done. A dot B the whole bar. Now you want to implement an AND gate. So firstly we'll implement a NOT gate. How do you implement a NOT gate using NAND gate? So I'll take one input line because not has only one input line. I have to feed it to what? My NAND gate. I should get complemented version of it. But again, I want two inputs. So what I'm giving the same input to the NAND gate. Right? So A and A. So what happens? You're doing AND. So A, and you're also doing NOT. A and A the whole bar. A and A will be A only. A the whole bar. So technically you're doing what? Not. Not. Very simple. Not. So technically, when you have a signal, when you have a wire and you want to knot it, you will just convert it. You will just connect it to the same NAND gate. I mean, receiving the same input in the both the inputs, right? Input lines. You will get what the complement out. That's it. Now, how do you make AND gate? Very simple. AND gate is just the NOT version of it. NOT version of it. So what you do? You first NAND it and then you NOT it. NAND and then NOT it. Just take the same input line and give it to the NAND. It'll give you what and is realized simply, right? So that is and then how do you make or? How do you make or? So we make a use of the De Morgan's law here. You know that A NAND B. Okay, so let's. This is just yeah, yeah. So you want to make an OR gate out of NAND gate. So what I'll do is I'll make use of De Morgan's law because I know that whenever I have an input, let's say I bar it, I have another input, I'll bar it. I'll bar the overall input also. That don't you think A bar dot B bar, the whole bar will give you A plus B? A bar dot B bar, the whole bar is A plus B, right? So I'm using that thing. So A, I'll take one input line. B, I'll take another input line. I'll bar both. How do you bar both? Just give it to the same input line and NAND. Same input line and NAND. Now these both will be what? These both have to be what? They have to be what? And bar. So technically NAND. So done. So this will realize what? OR gate for you. So if you're able to realize or and not, you can realize everything you want. But yeah, make sure it's minimal. But yeah, you can realize everything you want. The number of gates you use should be minimal actually. Okay. You can do that with XOR also. Just giving you a circuit for your reference. You can always play with it. Okay. So let's say A, B. We have to XOR both. We'll do what? We'll take a common one. Okay. We'll do and NAND here. We'll do NAND here. We'll do a NAND here also. Okay. Okay. And we'll do an overall NAND here. See what this gives you. See what this gives you. And this should give you an XOR. This should give you an XOR. Okay. For XNOR, what do? You do one more. This will be XNOR. Okay. So that is feasible, right? So just look at the circuit. Hopefully this should be clear. Okay. Just play with it around. Play with it around. Okay. I mean, by the time play with it around, I mean see what signal goes in respective positions and see how you can formulate that expression. That's it. Okay. It's all in your creativity. I don't know if you taught elaborately, so I'm not doing it. Okay. Now moving forward, let's try to do this. K-maps. Again, so K-maps, what do you do this? See, K-maps is a wonderful method. Okay, wonderful method to in simplifying logic expressions because you have the fixed methodology. You know how to proceed to the next step, right? So that is there. So how do you make it? It's a graphical method in which you display all the minterms. You put all the minterms in your expression to be one. Okay, all the max terms are put zero. Okay, and what you do? You'll group ones in such a way that the common ones can be cancelled out. That's it. Okay. Basically, you know what? K-maps is actually a Boolean simplification only. Okay. But Boolean simplification in its graphical form. Okay. Meaning you are trying to cancel out the common factors. But how do you realize the common factors is the question, right? In a Boolean simplification, you randomly do things, right? You realize common factors and so on. But in K-maps, you actually have a fixed methodology in identifying the common factors and simplifying them. So that's what is the thing, right? So you do this to minimize the number of terms and implicant. So you have a function like this. You want to implement this function. You will see what is each term is an implicant. That's it. Okay. So AB is an implicant, ABC is an implicant, BC is an implicant. That's it, right? Implicant is just one box. Right? That's that. Now, prime implicant. Talking about prime implicant, each mapping you do is a prime implicant. Okay, so I'll talk about mapping, but each mapping you do is going to be called as what? Prime implicant. And essential prime implicant is the mapping which contains at least one implicant or one box, one minterm. Okay, that cannot be covered by any other prime implicant. So you see here in this case, we just so we had ones random ones here and there. We just block these two, these two, these two. You should always pair it in two powers, 2 power 1, 2 power 2, 2 power 3, and so on, right? You can only pair it in two powers, right? Now, I paired it. I want to check which is an essential prime implicant. An essential prime implicant is one which contains what? The terms, okay? Uh, I mean, which contains at least one term which is not backed by any other implicant, which is not covered by any other implicant, right? Why am I telling it is essential? Understand, it is essential because if it is not going to be covered by any other implicant, don't you think it is essential prime implicant because we cannot neglect that prime implicant, right? EPIs are the ones which are important in an expression. Okay, when you reduce one full function into K-map reduced form, okay, whatever you end with, whatever terms you end with, those are all essential prime implicants because you cannot find a reduced form from a K-map without neglecting the essential prime implicants. But prime implicants is a generic term which talks about mapping, right? That is there. So you see, I'm just telling you how to map and how to take common terms out of mapping. We can maybe do it using four will K-map, and then we can because that will be simpler. If that will be simpler if you do this, right? So what happens here? So whenever you have a function, okay, see how many variables are there. So first point in solving these sort of problems is first thing, identify what is the input, identify what is the output, identify what is the process, right? What is the input? The inputs are four things, A, B, C, D, right? Four inputs are there. Four bits will come. Okay, great. What is the output? The output will be based on some function, right? Now, this function will follow some logic. Now, based on that logic, you'll assign the output, right? Based on this logic for each combination of that. So, if you have four things, what are the combinations available? 2 power 4, 16 boxes can be done, right? Then 60, using these 16 combinations, you can formulate your output based on your condition, right? Done. Super, very nice. Now, using these output lines, you will put one in each of these input lines. So, all these 16 boxes are represented in a concise format. You see here, 0000 is nothing but the input line 0000. For these 0000, the output was actually 1. For 1010, the output was actually 1. In all the other cases, all the other 14 cases, it was 0. That's why it looks like this, right? Now, so you saw that. Now, how do you do the mapping? Mapping is very simple, guys. So take all the adjacent terms, take all the edge terms. Edge terms as in something like this. These two are on the edges. You can map them like this, or if they are totally adjacent like this or like this, you can do that. You cannot do diagonally. You can only do horizontally and vertically, or along the edges, right? That is there. Understand different mappings here given here, so it will be very much easier. Now, how do you take the common terms? So you map these two, 1, 1. See vertically. See vertically what's common. Between 1 and 1, what's common? Vertically, if I see, this whole column itself is common. Column itself is common. What does this 0, 0 mean? This 0 means C takes C bar and D takes D bar. That's it. What does this 0, 1 mean? C takes C bar and D takes D. So this will be just C bar D. And this will be CD, this will be just CD bar. Very simple. So this will be just C bar D bar. And if you take along the horizontal line, it will be 0010. So what is common here? The left bit 0 and 1 are not common, but the right bit 0 and 0 are common, which is B bar. So technically, if you realize it fully, it is just B bar, C bar, D bar, right? So that's the thing. So I hope you can do this. I'm not emphasizing on the common terms now. Is that clear, all of you? Just can you just react quickly? Till this point, everything is clear. Okay, great. Now, the same thing. You'll just try to map these two. What is common the horizontal side B? What's common the vertical side is C bar D, right? So on, so just see the mapping. You can do mapping like this. You can do mapping like this. You can map all the four on the edges. You cannot map two on the edges, but you can map four on the edges. Okay. Um, I by the term mapping two on the edges, I mean diagonally. This is not possible. I mean even this is not possible. One sec. Yeah, even this is not possible. Okay, but all the four are possible, right? All the four are possible, and you can do two also on the edges. You can do two. You can do four here, right? You can so let's try to do this. So you can also take common here in this three variable k map. In again this convention, it's not necessary that you'll only take a b c. You can take a there. You can take b c. I mean, if you take a here, it will be like something like this. It will just look, the table will look like this. But okay, wherever you take, see what are the combinations of that input. So I take a here. A can be either 0 or 1. BC I take here. BC can be 0001. Understand it is not 1011, it is 1100, 1110 because of gray codes. Gray codes. Gray code format this is. Okay. Yeah. So understand that. Yeah. So let's try to map them around. So you see here, how can you map this? So let me try to visualize this. Yeah. So these two can be mapped, these two can be mapped, and this will be separate. This cannot be mapped with anything, right? And if it's separate, how will you take it? Just take the whole box. What is the whole box? It is just A bar, B bar, and then C. Simple one. Similarly, you can map this. How can you map this? See, I immediately see there's a 4 here, and immediately see there's a 2 here. That's it. Simpler one. I hope you can take the common out, and 2 and 2. Simple. And then there's going to be a 2. One second. Okay. POS and SOP in K-maps. So POS is product of sums, product of sums, and SOP is sum of products. All the things which we did now, mostly we'll do it in sum of products form only. We are only interested in min terms. But if you have a sum of product form, or a product of some form, don't you think you can always keep it in the sum of products form? Yeah, because you can just put once for all the remainings if it is a product of some form. So let's say you have something like this. Okay, you have, instead of giving sigma of, okay, 1 2 3 4, okay, they are giving, let's say we have 3 bits, so 8 things are possible. Okay, so 1 2 3 they have given. Okay, sigma of this you can just put in the respective places of 1 2 and 3, meaning 0 0 1 0 1 0 0 0 1 1. In all these cases you will put 1 in that box, and in all the other cases you will put 0. This is a sum of product form. But you want to realize this using, let's say they're not giving sigma, instead they're giving pi of 1 2 3. Pi of 1 2 3. If that is the case, what do you do? If that is the case, in all these cases, in all these cases, 1 2 3, you will put 0. In all these cases, you will put 0. In all the other cases, the remaining boxes are there, no? In all the remaining boxes, you will put what? 1. That's it. Simpler one. Okay. So that is the thing. Now, let's try to group two things, two things, and two things. Right? Simpler one. Four things together and then two things. Right? Let's try to map this also. You can group 4, 4, something like this. You cannot group anything here. This will be realized as single term only. Okay, you cannot group anything here, single term only. You can group 8 here, you can group 8 along this way, you can group 8 like this, you can group 8 along that. Okay, so just see all these mappings, just mapping techniques you have to see. You know how to take common, right? Now, similarly, let's try to do this also. 8 things bulk you can take it. Now, this I cannot group 6. I can only group in. No, no, no. For I am not complicating you in grouping zeros in POS data. Okay. Just I mean, you can just realize an SOP sort of form from. You can just reduce the expression from the SOP form itself. So what I respect, I mean, it's just for your trick. Okay, you can always do that. I don't want to teach you because it was never taught for us. But yeah, it is still easy. So what do you do whenever you have an SOP form or POS form, you can always convert it to an SOP form and do it, right? So, given SOP form, you can always put ones there and then group ones and do all, right? So that is there. Now, twos. and twos and twos, right? Very simple, because I cannot group six, right? Two only I can group. Similarly, I can group these two, right? One second. I can group two, can group two, I can group two, I can group four. One, two, three, and four. You see here? Very simple. Yeah, that I can do. Similarly, here four, two, and then two, and then two. Right? Simple. So you can do that always, right? So easier to realize. Now, how can you group this? You can group these four. That is the only possibility. You can group these four, right? You can group these four. That's done, right? So I mean, it's not necessary that every possible grouping has to be done. You have to group in such a way that all the ones are covered. That's it. Okay. So yeah, design a three input digital circuit that will give out its output a logic one. Only the binary number formed at the input has more ones than zeros. So these sort of questions are expected, guys. So how are you supposed to handle these questions? Very simple. First, take all the inputs. Three inputs are going to be there. So what are the possibilities? Starting from 0, 0, 0 till 1, 1, 1. That's the possibility. What is the output? Something 0 or 1. Okay. But what is the logic? It will give you only a 1 if it's going to be more ones than zeros. So see your input. More ones than zeros. No, more zeros and ones are there, right? More zeros than ones are there. More zeros than ones are there. More ones. See, two ones are there, one zero is there. So more ones than zero. So put one there. So in all other cases, just consider the logic case. Consider the logic. Put one there. Put one there. So where and all one is there? Where and all one is there? In 0, 1, 1, there's one there. So you construct a K map like this. Okay. You consider A here, B C here. Whatever you want, you can keep it there. A can assign value 0, 1. B C can be 0, 0, 0, 1, 1, 1, 1, 0. Now 0, 1, 1, it is one. So 0, 1, 1. You see here, right? 0, 1, 1 is going to be 1. Similarly, 1, 0, 1 is going to be 1. 1, 0, 1 is going to be 1. 1, 1, 1 is 1. 1, 1, 0 is 1. Now I can just do the mapping, right? So just do the mapping and get the value. That's it. And realize it using the circuit. I don't think that should be a trouble, right? So you can always do this. This is called majority circuit, by the way. Majority circuit. Okay. Meaning whatever is majority, that will come. If zeros are majority, zero is coming. If ones are majority, one is coming. So that's it. Okay. Yeah. Again, this is very simple. Again, you will put one when the number is between 2 to 9. So all the cases when it's 2 to 9, you put one there. All the other cases you put zero. And wherever one is going to be there, map it in the four variable K map. And then you can just construct the circuit. Till this point, any doubts? And also, don't guess. So talking about don't guess. So you will be given a question like this: 1, 5, 6, 11, 12, something, something, something. Okay. You'll put them and then you put one in all these cases where your small m is there. Okay. Whenever there's going to be a D, don't care. Okay. You put an X there. An X. Okay. You'll take X only when you care about it. We're all selfish here. Right? What happens? You'll only use that guy when that guy is needed. Yeah. So what do? You are going to make X there, irrespective of whether it's useful or not. You will put X there, but you will map only when it's useful, right? So this guy helps me in mapping all the four entities. Unless I have to map it in 2, 2, 2 only, right? So I can use this X, right? And I can just do my mapping corresponding to them. See, even in this four variables, he's useful, right? This mapping also, and this is really separately, right? So that is there. And observe this. Observe this. When you map just one box, you can't. When you just map one box, you will have four literals in your term. Four literals in your term. Okay. When you map two things, just one pair, like two boxes are mapped, then you will contain how many terms? Two terms. In a four variable K map I'm talking about. When you map three terms, you will contain how many terms? Two terms. When you map four terms, okay. Sorry. Um, sorry. One second. I mean, by the term, when you map 2 power 0 boxes, it will be what? Four terms. Okay. When you map 2 power 1 terms, just for confirmation, I'm telling. Okay. When you're taking common, you can just cross check, right? When you're mapping 2 power 1 terms, right? How many common are there? Three terms. Three terms, right? When you're mapping 2 power 2 terms, there will be two literals. By here I mean literals. Okay. And when you're mapping 2 power 3 8, you try to map this 8 thing. You try to map this 8 thing, let's say. Then let's say there are all of them are one, let's say. Okay. You try to map them. What is common? You tell me what is common. In the left, there will be nothing common. You see here? In the left, in the horizontally, nothing, because all the four combinations are covered. In the right, 0, 0, and 0, 1. Right? What is covered? The first one. So it will be C bar. So only one letter will be there. What if you map 2 power 4? 2 power 4 meaning 16. Everything is 1. So you'll get what? Nothing. Almost everything is covered, right? So it will be just all the min-terms together. All the min-terms together, right? So that is always there. Meaning what is that? That just means it does not contain literally, it just means that function itself is one. Function itself is one. That's it, right? If nothing is covered, function is zero. If everything is covered, function is one. Very simple, right? So yeah. So yeah, you can always do this. Um, Hope you are fine with this. Shall we move forward to third unit? If you have any doubts, feel free to reach out to me. Right? Till this point, everyone clear? Can you just react? All right. So we are moving forward with unit three. We'll just take some 2 minutes break. We'll start unit three. All right, guys. So moving forward with unit 3. So till this unit, we saw how to reduce terms, how to easily simplify your logic expressions, which contains a lot of literals. How to do mapping, how to take common expressions, how to do things, how to make logical circuits. This designing of logical circuits is very important in the next unit as well. So I've divided this unit in two parts. The first part being before encoder decoder stuff and after encoder decoder stuff. Okay, upon your request one. Okay, so we saw your feedback forms and stuff, right? So moving forward, combination logic circuit. I told you, right? A combination logic circuit. Just how do you design it? First, understand the problem statement. What is the input? What is the output? What is the logic behind it? Just formulate your output according to the inputs based on the logic condition, right? And then whatever you're going to have, simplify that using K maps. As simple as that, and draw the logical circuit. Now, see, you want to make a half adder. Very simple. First thing, what you do, you want to make the input output. What is the input? Well, you are going to, let's say, a half adder. A half adder takes in only two inputs. Only two inputs. Okay, a full adder takes three inputs. The same case for subtractors also, right? Now, you have two outputs also, carry and sum. Okay, so basically 0 plus 0, what is the carry? 0, sum 0. 0 plus 1, sum will be 1, you don't carry anything. 1 plus 0, you don't, sum is 1, you don't carry anything. 1 plus 1, you carry 1, but sum will be 0 because 1 plus 1 was 2. You put 0 in the sum and you put carry in the 1. I hope you all know it, right? So, how do you deduce the logical circuit for a specific truth table? You have to understand this methodology, unless we cannot move of this chapter, right? You can only deduce the circuit by seeing the ones. I mean, you can also do it by seeing the zeros by max terms, but I'm not talking about that. I'm only talking about min terms, right? So once you will see where one is there, if one is there in this particular row, what is that row actually? That row is the minterm which corresponds to x dot y, because actual variable is 1, which is x and y, right? So x dot y. So carry will be x dot y. Similarly, sum would be what? X dot y plus xy bar. You see this, right? So x dot y, sorry, x bar y plus xy bar, which is nothing but x XOR y. So you will just take two inputs. So this is a circuit. You just take two inputs, XOR them, you get what sum. You take two inputs, and them, you get C. Carry. Very simple. Same straightforward, half subtractor. Just realize the truth table. I'm not emphasizing you on making the truth table because you should be able to make it, but I'm telling you how to make the circuit, right? 0, 0. Difference will be 0. You're not you're subtracting anything. You're not getting anything from someone. You're not borrowing anything, right? Similarly, 0, 1, you have to borrow one thing. After borrowing, it'll be what? 2 minus 1. It'll be still difference will be 1. Now, 1 minus 0, difference will be 1. Borrow, you're not doing anything. 1 minus 1, difference 0, borrow 0. Now, just deduce the expression like this. The same way. It's just, okay. Oh, sorry, 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 sorry. Sorry, 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 sorry. Yeah. So, what happens here? This expression is given wrong. This expression is given wrong. I mean, sum is correct. So, it's not sum actually. Yeah. Difference. Difference would be nothing but x bar y plus xy bar, right? Similarly, the borrow would be nothing but x bar xy bar, right? Borrow would be nothing but, sorry, x bar y, sorry. Yeah, borrow would be nothing but x bar y. And this will be x bar y plus xy bar. That's it. So what do you do? Same thing. Take inputs, put them in the OR gate difference. Take the AND of A and B, sorry, not of A and B, you will get borrow. Simpler to understand, right? You can do that for full adders also. Same thing, same thing. Getting that? You see here, see the circuit here? Put the carry, put all the sums. Wherever one is going to be there, realize the corresponding minterm, and you can also simplify the minterm. So in this case, I'm just getting this expression a bar b bar c plus a bar b c bar and so on and so forth. So two bar at a time, right? And we also saw in the initial part, we saw, right, carry of the full adder, one bar at a time, a bar b c plus a b bar c plus a b c bar plus a b c. That is going to be carry, right? And you can, so also we reduce this. Remember, we reduce this to ab plus bc plus ca, right? That is also doable, right? That is one of the ways you can do it, right? There are other ways, right? You can implement a full adder using two half adders. What is a half adder? A half adder contains what? Half adder contains an OR gate, an XOR gate, and an XOR gate, and an AND gate, right? So what happens? You have X, you have Y. This will be X XOR Y. What is this? This is the sum of the first half adder. Okay? Now, you have one AND gate, and this is the carry of first half adder. Okay, very nice, super. Now, why am I doing this? Blah blah blah. Something, some line is going here. Ho ho. Nothing but it's the same expression. You see here. You see here. What happens here? What happens here? You see A bar BC plus A B bar C plus A B C bar plus ABC. Okay, super. I immediately when I see this, my mind goes like this. I want to group AB so that I can free up. One second. One second. I want to group AB so that I can free up what C. So AB to C bar plus C is just one. What goes in your mind when you see this? A bar BC plus A B bar C. I see C is common. I can take it outside. So C into A bar B plus A B bar. Wow, nice. This looks like something. What is this? A bar B plus A B bar is the sum of what? The first full adder, right? So technically, you take the sum of first full adder and it with the third output, you will get one thing, right? You will take that line. And you take, what is AB? AB is the carry of the first full adder. You take that also. You take both and you R it, you get the carry of the for the overall full adder, which you did using two half adders, right? So this is, sorry, I was talking about half adders. Yeah. So this will be x x r y. This will be xy. You take xy, directly put it because AB was directly put it, right? Now this line was only the one which wanted attention. You took the ax or b, you put it here, and then you took the third line, you put it here, and it and then put it here, and overall or will be realized as carry, right? So two half adders put together, and you'll give the carry from here to directly here, and you'll give the sum here, and you will get the final sum here. You will put the carry here, and you'll get the final sum here, right? So final sum and carry will be easily realized, right? So that is the case. Now, you have binary adders. We know all this, right? Now, ripple carry adder. What happens here? This is a type of binary adder in which you want to add multiple bits. Okay, you have a number A0, A1, A2, A3. You have another number B0, B1, B2, B3. All these are binary numbers only. You want to add both of these numbers. What do you do? First, you will add A0, B0. It will give you one sum. It will give you one carry. You will give it to the next one. You will add A1, B1. It will give you a sum. It will give you a carry. You will give that sum to the next one. A2, B2, S2, C3, A3, B3, S3, C4. Understanding the logic, right? So carry is actually rippling through. You understand this? That is why this is called ripple carry adder, RCA. Okay. So ripple carry adder, 4-bit adder, whatever. Right. So carry is going to be rippling through this. Why do you call it rippling? Because this guy, this guy is Pavam guy. This guy has to literally wait until this guy completes. This guy will wait until this guy completes. This guy will wait until this guy completes. Why should I wait? Because I can only compute if I know that carry rate. I can only compute if I know that carry rate. Without knowing what the carry I got, I cannot do A1 plus B1 plus C1. Right? So that was a problem there. So that was a 4-bit address problem, ripple carry address problem, for which you have something called what? Carry propagation. What is that? CLA. Yeah. Carry look ahead adder. We are not going to that deep. Don't worry. Don't worry. It's not there for you, I guess. But it's a wonderful concept. I would love to teach you. If you want to really want to learn from it, you can always ask me. Yeah. But yeah, this is a wonderful concept. So you because what it does is it will calculate. It will pre-compute all the carries. What do you mean by pre-compute all the carries? They are telling me that all the carries C2, C3, C4, everything, right? These are not necessarily only dependent on A1, A2, A3, B3, and so on. These are actually coming from A0, B0, no? Right? So from A0, B0 and stuff, okay, from A0, B0 and stuff, A1, B1 and stuff, you can actually compute C2, C3 directly. There are separate units called propagation unit, generation unit under a ripple carry adder, which will do it for you and it will just do it. No need to worry about it if you don't understand. I'm just telling you the concept that ripple carry adder is having a delay, right? It has a propagation delay because nth full adder has to wait for n minus 1th full adder to complete the operation to get the carry. And each thing has a logical depth of two gate levels, AND gates and OR gates, two gate levels. Okay. And for an n bit, ripple carry adder, because one full adder does two gate levels because AND gates and OR gates, n bits full adder, n full adders will be required. Right, n bit ripple carry adder, n full adders will be required. Here, 4 bits, 4 full adders, n bits, n full adders. So, 2 n gate levels will be required, 2 into n, right? Each full adder, two gate levels. That's it. Okay, so that's it. So so yeah, carry look ahead adder is useful. Now, moving forward. This is another wonderful circuit. See this. See a binary adder subtractor circuit. What happens here? You see, you have a mode input which will help you which will help you in deducing whether this is going to be a subtractor or an adder. Okay. So firstly, this mode input is set. Okay. Nice. Both adder and subtractor can be done in the same circuit. Wow, wonderful. Nice. Super. So what happens? Let's give zero first. Let's give what? Zero. When the mode input 0, what happens? 0 is given here, 0 is given here, 0 is given here, 0 is given here, right? Now, because 0 is given here, what happens? So A naught is directly passed to the full adder. So this is almost same as the what? My 4-bit adder, triple carry adder. Okay. But what is different here? Only P naught. You see here, A naught, A1, A2, A3, same thing, right? P naught, B1, B2, B3, they are different, right? So you have to deduce a method in putting those bits in a different format for making subtraction also, right? Firstly, we'll see addition how it works. So what happens? B naught and 0, both are what? XOR. What happens when you XOR? I just told you there, I told you there, right? B naught XOR 0 would be what? Just B naught, just B naught. So B naught goes there, B1 goes here, B2 goes here, B3 goes here. Wonderful, super, works like very nice. What? Adder. Okay, nice. What happens when you give 1 there? What happens? You give 1 here, what happens? Let's try to deduce this logic. Okay. Yeah. So if more input is going to be 1, what happens? Firstly, earlier 0 is going here, no issues at all. Now 1 is going to the first input carry. This is called input carry by the way. Okay. Carry in, right? So 1 goes here, 1 goes here, 1 goes here, 1 goes here. What happens? You are actually doing B3 XOR 1. B3 XOR 1. What happens when you give 1? We saw there. We actually saw there. The complemented version will come. B3 XOR 1 will be B3 bar. So this will be B3 bar. This will be sorry, B naught bar. This will be A naught. Similarly, this will be B3 bar and this will be A3. And actually, what I'm giving here, 1. Technically, I understand. A naught plus B naught bar plus 1. What is that? What is that supposed to be? A naught plus B naught bar plus 1. B naught is one number. I'm barring it and adding it to 1. What am I doing? I'm doing 2's complement. If I'm doing 2's complement, what does it mean? Actually, I'm doing subtraction also. Subtraction also. Right? So that's going to be what? A minus B. A minus B. You understand the circuit? All of you, can you please react something? Right? So when you have mode input 1, you just put it here. Now B naught plus 1 would be just B naught bar. So A naught plus B naught bar plus 1 would be just A naught minus B naught. Understanding that? Everyone, can you please react, please? Others? Yeah. And you use yeah, so repeating it once again. So adder, you'll use adders whenever your mode input is going to be what? 0. So when your mode input is going to be 0, the whole circuit acts like what? A complete 4-bit adder. Complete 4-bit adder. It's the same circuit because you do XOR 0 with anything. It's the same thing. So you see here, one second, one second, one second. Yeah. Here you have B naught. B naught is passed to this what? XOR gate. And what is the other input here? The other input is 0. 0 XOR B naught will give you what? B naught only. So A naught, B naught, S naught, C1. A1, B1, S1, C1. A2, B2, S2, C3. And so on. You are getting this context? React? Now, moving forward with subtraction, what happens? Mode input is 1. If mode input is going to be 1, you will pass 1 here and every XOR gate will receive what? 1, 1. Right? 1. So, 1 XOR anything will give you the part of it. 1 XOR B naught will be B naught bar. B1 bar, B2 bar, B3 bar. So B naught bar plus A naught plus 1. What is that? B naught bar will be 1's complement. 1's complement plus 1 will be 2's complement. A naught plus 2's complement of B is nothing but A minus B. Right? So subtract. And that is the full logic. So you can do it for all the 4 cases. Right? So that is the whole logic. And this is used for finding the overflow. Overflow is nothing but when you have a certain number of bits to be accommodated, but you're accommodating more bits, you cannot do that, right? So some kind of logical error is there in the overflow. So what happens? C4 and C3, you'll check if both are going to be same, it'll give you 0, right? Because XOR gate does that. If even one of them don't match, then it's going to be 1. So your this P is going to be the overflow detector, which will check whether overflow has come or not. Right? So that is the case. Not too much on it, just brushing up. Okay. Now, overflow is a problem in which n plus 1 bits cannot be accommodated in an n bit system. Right? Now, when two unsigned numbers are added, an overflow is detected from the n carry. So you are adding two numbers. which are unsigned, meaning you're not talking about signs and all as of now. They're just two positive numbers, right? When you add it, you just get n carry. That is not that is the overflow which is directed from the n carry. Super, very nice. When two sign numbers are added, right? When you to add to sign numbers based on the systems which we discussed, right? Sign the system we discussed, no, one's complement, two's complement, and sign magnitude. When you do that, then that n carry will not indicate what overflow, because that is going to be the sign bit. That also we saw there, sign bit. An overflow cannot occur if one is positive, other is negative. Very simple analogy. If one is positive and the other is negative, you do anything on it. If you do anything on it, that will always return what? That will always return a lesser result, because one of them will cancel out, right? So a minus b, it will always be lesser than two of the numbers. So why would overflow occur, right? Only if greater overflow will occur. An overflow may occur if the two numbers both added both are positive or both negative, right? That's true, right? If one of them is positive and the other is negative, overflow cannot occur. Now, simple binary multiplier is here. Very simple. You see here. So you want to multiply a naught a1 with b naught b1. So how do you do it? Normal multiplication. A naught b naught, a naught b1, a1 b naught, a1 b2, a1 b1. Right? You will just keep this. It's c naught. This will be c1. This will be c2. I mean, technically s naught, s1, s2, s3. These are all sums, right? Partial sums. Now, partial products added together, right? So these are all called partial products, by the way. Okay. So how do you deduce this? Very simple circuit. What do you want? A naught B naught should be directly going. So A naught B naught directly goes to C naught. You see here. Now A naught B1 and A1 B naught should be added. So what do you use? Two inputs are there. Simple half adder will do, no. So A naught B1 first I'm doing using an AND gate. A1 B naught I'm doing using an AND gate. I'm passing both to a half adder, and I take the sum over there and I pass the carry to the next one. Right. Same thing. A1 B1 will be generated, and the carry from the previous one will be put into the same half adder, and you will generate a sum and a carry. So this will be the entire one. This will be the entire answer for this binary multiplier. So that will be the output. Clear till this point, everyone? Everyone is clear till this point? Can you please react? Okay, okay, great, fine. Now, 4-bit by 3-bit binary multiplier. So what do you mean by this? So you are multiplying something by something, right? So how do you do this? So understand, when you multiply 2 into 3, you are multiplying 2 by 3. Okay. Meaning 3 is going to be multiplier, 2 is going to be multiplicand. You are multiplying 2 3 times, right? So 2 by 3. So if you are multiplying j, so for j multiplier bits and k multiplicand bits, multiplicand is something with which you are multiplying something, right? So two, in the case of 2 into 3, right? What happens? You are multiplying 2 3 times, right? So in this case, you are multiplying k j times. So j multiplier bits and k multiplicand bits. So how many AND gates will be required? J into k AND gates and j minus 1 k bit adders, right? So we'll see a simple example. You are multiplying you are making a 4 cross 3, 4 by 3, right? So multiplier will be nothing but 3, and multiplicand will be 4, right? So how many AND gates will be required? 4 into 3, 12 AND gates. 12 AND gates. And how many k bit adders will be required? J minus 1 k bit adders. What is j? J is 4. So 3, j is 3. So 2 4-bit adders will be required, right? So that is it. So this is a simple array multiplier concept. Right? So what happens? We'll just generate all the terms. Firstly, what do? You will have B0, B1, B2, B3 as a multiplicand. You are multiplying that with A0, A1, A2, right? What do? First, generate the initial set of products. How do you generate it? You will have A0. The last bit will always go directly. So A0, B0. It just goes on. The remaining ones, A0 B1, A0 B2, A0 B3 will go to the 4-bit adder. Similarly, A1 B0, A1 B1, A1 B2, A1 B3. That will also give to the 4 adder. And you will pass 0 as total 8 things will be going on, right? Input carry, right? So you'll have 4 things. You'll have 4 things here. That will be a full 4-bit adder. And you'll have 4 sums coming out of it, right? 4 sums coming out of it, right? And from this 4-bit adder, you will have one thing coming out of it. Remember, you'll always have that one thing. The last line will come out, right? So that will come out. Now this is done. Here for the remaining 4, and you put in the 4-bit adder. That will give you that will give you 4 inputs, and that will give one carry. Okay. I hope binary multipliers are there. Isn't it not there? Anyways, just learn the concept. You should be able to make any circuit out of this. Very simple. Just adders, 4-bit adders. Just put some AND gates. Deduce the logic by just putting respective products into the adder, that will generate the sum for you, and you can use that sum to generate more sums for you. Right? So that's the thing. Magnitude comparator, I think this should be there. Very simple circuit. Okay, very much nicer circuit actually. See, you want to compare two numbers. You want to compare two numbers. Let's say the two numbers are A naught, A1, A2, and A3. The other number is B naught, B1, B2, and B3. You want to compare these two numbers. How do you compare? What do you mean by magnitude comparator? Which one is greater than which one, or which one is less than which one, or which one is equal to which one? That one, right? So, how do you compare? You always go for the first one. So, when you compare 125 and 636, how do you say? You always see the last first one. I mean, the MSB question, right? 6. Oh, nice. Okay. 636 is bigger. So, similarly, you'll always check the first. So, you'll check whether A3 is bigger or B3 is bigger. Okay. So, let's first do the equality condition and then we'll go for the bigger condition. When do you say both are equal? There is a gate which helps you in predicting this equality. What is that gate? We were talking about some gate which gives you a result based on whether two things are equal or not. What was that? That was XOR gate. XOR gate gave 0 when both things are what? Different. But I don't want different. I want something to give me 1 when something is same. What was that? Just reverse it. XNOR. XNOR. Use an XNOR gate. So XNOR gate is utilized in this question to compare two things, whether they are same or not. Right? So when both these numbers have to be same, what do you do? A3 XNOR B3, right? A3 XNOR B3. A2 XNOR B2. If both numbers have to be same, all the bits have to be same. A2 XNOR B2. And so this should be what? And dot. So dot A1 XNOR B1 dot A0 XNOR B0. So this will be the expression. And this circuit again is simpler only. I'll teach you that also. But yeah. So this logic should be clear, right? Now, similarly, how do you make it for A greater than B? What do you mean by A greater than B? What are the cases, possible cases for A greater than B? Either A3 should be greater than B3. What do you mean by greater? You have only two bits. So one of them should be 1, the other should be 0. So A3 should be 1, B3 should be 0. So how can I write this? A3, B3 bar, right? So this is one case, right? If this case is true, it will always be true, right? A will always be greater than B. Plus. Okay, nice, super. Or, so plus I put because or. Or what is the other case? A3 and B3 can be equal. A3 and B3 can be equal. So how can you write the equality condition? A3 X nor B3 and then A2 B2 bar. A2 B2 bar, right? Similarly, this is one of the cases, right? Both of them are equal and you can say A2 B2 bar because A2 will be what? 1, B2 will be bar 0. Now, what is the other case? Both of these bits could be similar. A3 X nor B3, A2 X nor B2. One sec. A2 X nor B2 and A1 B1 bar. A1 B1 bar. Right? So that is one of the feasible ways to do it. Right? Or you can do the last option. All the three things should be what? Equal and then A naught B naught bar. Very simple. So that is the whole thing. So they have generated all the terms like this. So you should see here. So the circuit Lucas, they have generated all the terms beautifully. So what they have generated, you see here. Yeah. If you understand the circuit, it should be clear. So what happens here? A3, A3 bar. Now here B3 comes. Here A3 comes. Here B3 bar comes. What are you doing? You're adding it. So what that will return what? A3 bar B3. This will return what? A3 B3 bar. You're going to OR it, NOR it actually. So A3 bar B3 plus A3 B3 bar. Right? So that is going to be the first A3 XNOR B3. Right? This is A3 XNOR B3, A2 XNOR B2, A1 XNOR B1, A0 XNOR B0. So circuit understanding should be clear, right? So you have generated literally all the XNORs, right? So XNORs are done. But what is the logic? Firstly, A equal to B logic. What is that? Your four lines are coming. Why are four lines coming? Four things should be satisfied. What are the four things? All the bits should be same. That's it. All the bits same. So what do you do? We saw x1, x2, x3, x4 lines, right? All the four lines should be what? Satisfying the condition. So you will put an AND gate satisfying all the four conditions. What are the four conditions? X1, x2, x3. You see the first line comes from where? You see where does the first line come from? It comes from this line. What is this? This is x3. This is x3, right? This is x3. Similarly, the second line comes from x2. You see, this is the second line. This is second line, x2. Simply x1 and x0. All the four conditions should be equal. If it is a greater than b, what is the case? See the first line. The first line goes from the x1. Why x1? Because that was the first thing you wrote. Because if you two numbers are equal, either the first number is equal. A3, sorry, first number is greater. First number is greater, sorry. So first number has to be greater. So let's take this line. A greater than b. Then a greater than b, what is the logic? Either A3 should be greater than B3, meaning A3 B3 bar, or A3 and B3 should be equal, and then A2 should be greater than B2, A2 B2 bar, and then A3 and B3 are equal, A2 and B2 are equal, and then A1 is greater than B1, A1 B1 bar, and then all the three A3 XOR B XOR B3, A2 XOR B2, A1 XOR B0, B1, and then A0 B0 bar. Right? So that's it. You will just use the XNOR gates and stuff, right? So what happens here? So you see here, A greater than B, you want that logic. So you will take the first one. Where does this come from? This comes from what? This comes from this line. This line. One second, one second. I'm not able to come. Yeah, this line. So this line is where it comes from. What is this line actually? This generates A3 B3 bar. This generates A3 B3 bar. Beautifully it generates it. So I'm taking the first one, A3 B3 bar, easily. Done. Super. The second one is what? Second one is A3 XNOR B3, A2 B2 bar. A3 XNOR B3, A2 B2 bar. So where is that? The second line comes from where? It goes. Okay, it stops here. What is this? You see, it takes the X1 line. X1 line is nothing but A3 XNOR B3. For convenience, I've written the X1, which is nice, right? And second one, what is this? This is A2 B2 bar, right? A3 XNOR P3, and A2 B2 bar will go there. Similarly, the third line will come from what? This AND gate. This AND gate. So if you fully understand this circuit, it will be clear. You should go through this PPT once after this session, right? So A3 XNOR B3, this will be X3, and this will be X2 because A2 XNOR B2, both of them should be equal. And then this will be X, this will be what? This will be A1 B1 bar, and so on. So I hope this is clear. And for less than, it's the other way around, right? Wherever bar comes, the bar won't, the bar will come in the next one, right? Because it's nothing but A less than B is nothing but B greater than A, right? So it's just the same logic. So up to you. So till this point, everyone is clear. Till this point, everyone is clear. Can you please confirm? Please react. Can you all please react? Okay. Okay. Great. So we'll be talking about decoders using these slides also. We'll also be talking about decoders using other set of slides which we have. Okay. So yeah. So decoders are just minterm generators, as simple as it. Okay. Decoders generate minterms. You give any sort of inputs, it will generate two per n outputs. Okay. So if you have three inputs, it will generate two per three, which is eight outputs. For each possible input combination, there are seven outputs that are equal to zero and one output that is equal to one. So what happens here? You see what happens? You have x, y, z. These are the three inputs. You will also bar it, x bar, y bar, z bar. What are the possible inputs you can get? 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on, right? Till 8, D0 to D7, till 8 things you can generate. When when it is going to be 0, 0, 0 combination, what is the midterm it is? What midterm is this? X bar, y bar, z bar. Then D1 will turn on. Okay, you can also name this as D0 to D7, but okay. For convenience, okay, actually for convenience, it should be D0 to D7, but okay. Yeah, they have named D0 D7 here, but okay, fine. So it should be 1 here. D0 should be 1. Similarly, if it is 0, 0, 1, D1 should be 1. D2 should be 1. D3 should be 1. And D7 should be 1. You're getting that right. So based on that combination, the corresponding minterm signal will become 1. Exactly. Okay. So that's decoder. Some decoders are constructed with NAND gates. It becomes more economical to generate the decoder minterms in their complemented form. So it's good that you complement your minterms in good format. So you can also do the other way around. Basically, it's the same thing, but instead of ones in specific things and zeros everywhere, it will be zeros in the specific things and ones everywhere. That's it. Just and it off. Here you had and, here you not it. That's it. And here you not it. That's it. Okay. And enable is there for enabling things out. Okay. For if enable is going to be what? In this case, if enable is going to be what? 1. If enable is 1, this becomes 0. If this becomes 0, none of them will work. None of them will work. Meaning, irrespective of whatever A and B is, D naught, D1, D2 will always give you what? D naught, D1, D2. Because this is a NAND gate, I mean, by the time none of them will work, AND gate will not work. But NAND gate will be what? 1, 1, 1, 1. Got it, right? Got it. So, that is there, irrespective of what is there. So, yeah, they will work only when enable is set to be 0. In this case, in that case, enable has to be, if there is an enable signal and you connect it to there, directly you will connect it, right? If there's a NOT gate here, it's as a reverse logic. Hope you understand that. Yeah. Similarly, 4 to 16 decoder using 3 to 8 decoder. How can I do it? 4 to 16 decoder. So technically, the overall circuit should contain 4 inputs and the overall circuit should contain 16 outputs. But how do you make it using simple 3 to 8 decoders? Firstly, you take the first three inputs, generate 8, generate 8. You take the fourth input as what? Enable. Take the fourth input as enable, right? And you take the complemented thing as the other enable. So if you are supplying three things for when you are supplying these three things, because you understand, right? Two for four things. So it will start from 000, it 0001, 0010, and it will go down go until 1111, 1110, and so on, right? So in this half, it will be the first bit will be zero. In this half, the first bit will be one, right? So technically, you can keep the enable bit 0 in the first eight, at midterms, and then you can keep the remaining in the 1 in the first thing, right? So 0, you see here, the not gate is applied to the enable of this, not gate is not applied to the enable of this. So technically, you're generating the same set of midterms in all the things. But because 0 and 1 configuration is there, 16 midterms are generated. Very simple. Hope you all clear. You all are clear with this. Okay. Okay. So, sum would be what? XYZ is equal to sigma 1247. Now, you will take all the 1247 lines. See, I told you decoder is simple minterm generator, right? Now, here minterms are generated. I want someone carry expression. I know what is the expression. I know how to deduce this because I can just make the truth table. From that, I can reduce the expression and I can put this in the form 1247. Very nice. Now, if I'm able to do this, then I can just, if I'm able to generate the minterms itself, I will just put them into OR gate. That's my logic, right? My logic is just sum of midterms. Midterms is generating. Just put them into OR gate, you'll get sum. Put them into OR gate, you'll get carry. Simple, no? So yeah. Now encoder. Encoder does the reverse, right? So for corresponding input signal being one, corresponding output signal is generated 000 001. If D naught is one, then 000. If D1 is one, 001 will be generated. If D7 is one, 111 will be generated. Super. Now you know how to make this truth table. Very nice one. Now how to I mean you know how to make the circuit also because you know where to see one, and wherever one is going to be there, you see you make the minterm configuration of that sort, and you will just connect them using OR gates, all the lines using OR gates, all the ones wherever it's going to be there, you make all these corresponding rows as minterms, and you'll just what connect all the minterms via sum, just OR gate. Okay. Now why do you talk about priority encoders in the first place? See, I told you when one of the input signals 1, it is going to give you the corresponding respective configuration of ABC. Okay, very nice, super. What if two things are there? There's a glitch, no? There's a glitch, no? Also, even if nothing is there, even if nothing is there, right? Even if nothing is there, still the output will. So what happens here? If two inputs are active simultaneously, the output produces an undefined combination. That is one thing. So you have to establish a priority, right? Another thing is output with all zeros is also generated zero. Output with D naught is 1 is also generated 000. Understand that? Output with D naught 1, right, was also 000. If everything is was 0, that was 000 only. Ambiguity, no? Which one is 000? So that was also there. So what you do, that's why you establish two things. One thing, input priority for the first issue which we addressed. Second thing, valid bit. Valid bit. Okay. Valid bit says if all the inputs of mine is 0, I'm not going to consider the I'm not at all going to consider this case. Okay. I'm not worrying about it. That's it. Okay. So in the case, irrespective of whatever X and Y I'm going to get, I don't care. My V will always be 0. So I'm not going to record that condition itself. Okay. Now, what happens when you have this case? When you have um, D naught, when you have D naught as 1, then obviously if D naught is 1, these are all 0, no worries, 001, good configuration, okay, fine. And when you have D1 1 and D naught, what do you mean by X? This X corresponds to anything. Anything meaning all the values X can take, 0 or 1. This does not talk about don't cares, don't worry. Okay. This X does not talk about don't cares. This X is actually condensed form. Condensed form meaning it can take any values. Meaning you can write this truth table as what? 0 1 0 0 also, 1 1 0 0 also. This X can be 0 or 1. Okay. So that is feasible. So if this is going to be 0 or 1, what is going to be there? Irrespective of whatever D naught is, if D1 is 1, I will always put what? One's configuration. What is one's configuration? One second, one second, one second, one second. What did they do? Okay, okay. They've mixed it. Okay, okay, okay. They mixed it up. They mixed it up. So, what happens here? The logic you should understand here is irrespective of whatever your input priority is going to be, irrespective of use of all decoders and encoders, a lot of plenty of use cases are there which we are not discussing as of a whole. I mean, it is used in a variety of circuits you might not have seen that in the sequencer circuit, but again sequence circuits are implemented using few things. Decoders and encoders are used in various you know um, logic applications. So we are not using this much because we are much more into the theoretical aspect, and that's not necessary as well. Yeah. So yeah, when d naught is 1, you put it as what? 0 0, right? When D1 is 1, you put it as what? 0 1, irrespective of what D naught is going to be. Similarly, when D2 is 1, you put 1 0, irrespective of what D naught and D1 are going to be. When D3 is 1, irrespective of whatever D naught, D1, D2 are going to be, you put always 3's configuration, which is 1 1. And valid bit will always be 1 in this case, then only it will be recorded. If it's going to be 0, irrespective of hardware, I don't care. I don't care. These two things are don't care, right? And based on what, where, so you can put this truth table actually. You can put this truth table. It will contain all the things, right? So 4-bit priority encoder. So you can just always make this game up. Wherever. So put this in the 16-bit configurations. Put all the things, right? And you can always write. In this case, is it possible? In this case, since we have 4 bits, I don't know if we can make it fully, but yeah, you know where it comes. You know where it comes, right? So wherever one is going to be there, mark those positions and put the don't case in respective positions, right? So in this case, what happens? I want to deduce a circuit for X. I'll see where X gives you one. X gives you one at these places. Where and all? D naught, D1, D2, D3, D naught, D1, D2, D3. Okay. So in this case, it will be just D2 bar, D3. Sorry, D2, D3 bar. So what happens? Sorry. What do I mean by this condition? Sorry. So what happens? X is 1, XX 1 1 1 0. What do I mean by this condition? XX is 0 0 0 1 1 0 1 1. All these values XX can take. You will consider all these cases and put 1 to all these cases. That's how you deduce this, right? So 0 0 1 0. You will consider that case 0 0 1 0. Where is that? Here. Put 1 there. Similarly, 0 1 1 0. Where is that? 0 1 1 0. Put 1 there. Similarly, 1 0 1 1 0, where is that? 1 0 1 0, put it there. 1 0 1 1, put it there, right? And do that for all the cases, for all the x's, and deduce that came up and find the expression of d naught with respect to what? D naught, D1, D2, D3. You can find what? X, Y, and B. Okay, not so tough, right? Till this point, clear, guys. You need not go too much into this. They won't ask this, but yeah, you have to understand how to build circuit. If you're doing digital listen, you have to know that. Till this point, okay? Can you please react? Okay. Now, mux. Mux is a selector. Okay. Mux is a selector. What do you mean by selector? Based on my select line, I'll choose one input as my output. That's it. Based on my select line, I'll choose one input as my output. Now, you consider this. This is a simple 2 cross 1 mux. Meaning two input lines are there, one output line is there. Based on my select line, I'll choose that. If the select line is 0, so what does this mean? If the select line is 0, I naught will go as y. If the select line is 1, I1 will go as y. That's it. Very simple. Right? You can make the truth table for it. You see this? If the select line is going to be, okay, let's make this 4 cross 1. Okay. So this is a 2 cross 1 thing. If the select line is 0, y will be I naught. If the select line is 1, y will be I1. So how can I make it? I can make a simple circuit like this. I can make S bar I naught, where it will be there for y. And I can make S and I1, yeah. S bar I naught plus Si1 will give me what? Y. Very simple. Now you can do that for a 4 cross 1 mux also. How can you do that? You will take four things. What you'll take? You will first consider two select lines. Whenever you have whatever number you are going to have this, log to the base 2, you have to take select lines. Or how many select lines you have? 2 power select lines will give you the number of inputs. Number of inputs, right? So here 2 select lines, 4 inputs. Now take all the combinations. Take all the combinations meaning S1, S1 bar, S0 bar. Okay, super. Now what I'll do? I'll connect S0 bar and S1 bar to the first one, and I'll connect I0. I'll connect S1 bar, S1 bar and S0, because S1 bar meaning 0 1 configuration. 0 1 configuration, I1 will get selected. 1 0 configuration, I2 will get selected. 1 1 configuration, I3 will get selected. So based on that configuration, things will differ, right? So understand that. Here, if you consider what is the input for this AND gate, I3 goes, yeah, sure. Now S1 will go, S0 will go. So 1 1 configuration, I3 will be coming. Okay. In all, see, if you keep it as this case, no, all the other AND gates won't work. That is the thing, because that's why one input will be selected as output. If you really go, if you're interested, please do this. uh, whatever other input lines are going to be there, check what happens when you give S0 and S1. So let's say I'll do one for you. You are keeping 0 0 here, right? And for that the I0 line was working, and all other lines are not working. How is it not working? 0 0. Okay, now you give 0 here, it will go here, it will go here. This will be 1, this will be 1. So these two lines are 1, these two lines are 0. This line is 0, this line is 1, this line is 0, this line is 1. Okay. Now whatever lines are 0, observe that. 0. Which line becomes 0? This line becomes 0. Okay. Which line becomes 0? This line becomes 0. Okay. And which line becomes 0? From this line, it was 0. And that 0 went on here. This line also becomes 0. So technically, all these AND gates will give you 0 only. And only this will give you what? Because it's going to be this will give you what? So because this is going to be 0 and this input line is 1 and this input line is 1, both those ones only go there. You see that? And that's why I0 was selected, because I0.1.1 will be just I0. So yeah. So simple understanding of that circuits. I'm not having the time to do the implementations of this. Okay. Implementation of higher order muxes using lower order muxes. I told you the logic to do that. Okay. It's totally up to you to practice those. Okay. I'll just show you some models. Okay. I don't know if I have time to do everything. I want to complete this quicker today. I'm not able to. I won't do this like math. Sorry. But yeah. So yeah. So what happens here? You can multiplex circuits can be combined with common selection inputs to provide multi-bit selection logic. Again, not so much of importance, but yeah. What happens here? You can try to generate all the other things based on your select lines again. The same thing. This is enable. Enable, whenever enable is going to be one. So because enable was with not, yeah, enable was with not, yeah, because enable was with one, it becomes zero, and all the things will be zero only, all zeros, irrespective of whatever my select line is going to be. If you want tomorrow, yeah, we can make this right. And whenever enable is going to be zero only, we will see what comes, right? When enable is zero and select line is zero, I'll select what? A, because enable is zero, select line is zero, so this will become one, the whole line will become one. Only this will work, right? Only this will work. No, this will not work. Similarly, you will say, so A will be selected, right? B will not be selected. So this is how you can generate whether I want to give A not A1, A2, A3 to the circuit, or B not B1, B2, B3 to the circuit. Amazing logic. See this, right? Same thing. Enable is zero and S is going to be one. If enable is zero, okay, everything will work because it will be knotted. Everything is one. Now X is going to be what? One. When S is going to be one, if this is 1, this will be 0. If this is 0, this will be 1. If this is 1 and this is 0, this is 0, so everything will turn off. So A will not work. And this B will work, everything in the B will work. This all will work, right? So that is the logic here. Yeah. And you can implement various functions using MUX, because MUX is called as what? Universal Logic Circuit. Okay, universal logic gate is NAND and OR. Universal logic circuit is MUX. Okay. So you take three input lines X, Y, Z, take all the combinations of it. Okay, you will try to at least keep one select line, because see, you want to implement this using a 4 cross 1 mux. 4 cross 1 mux meaning you'll get 4 inputs and 2 select lines. You'll get how many inputs? 4 inputs and 2 select lines. What I'm doing, I can do this in many ways actually. Here they implement using 4 cross 1. I'll just show you that. But what happens here is you will choose, you will you will prefer to choose one thing as select line. Here they have chosen two things as select lines, and they have regarded f and z as functions of 4. So that you'll have four, literally four inputs, and you'll have what? One output. Getting that logic, right? So x and y are chosen as select lines so that 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 1. So based on that, f will operate on z, right? So based on that. So you compare f and z bits. You compare f and z bits. Are they same? Okay, wow, f is z. Are they complemented? F is Z bar. Wow, nice. Irrespective of whatever, the F was always 0. So F is 0. Irrespective of whatever, F was always 1. So 1. So you will put them, you will pass them on to the inputs. Z bar 0, 1. Very easy. Very easy. And that will be the inputs. Based on the select line configurations, your function will reduce the output. Easy truth table implementation. Right? Same thing. Let's do this for the here also. Function is one big thing like this. First, write all the combinations and put ones wherever they say it is going to be 1. Yeah. Now they want to do this using 8 cross 1 works. Now 8 cross 1 works meaning how many inputs can you take? You can take 8 inputs. How many output will you give? You will give only one output. If you're taking 8 inputs, don't you think you have to have 3 select lines? So I'm taking A, B, C as 3 select lines. A, B, C as 3 select lines. And you are going to compare F with D. F with D, right? So F in these two, you are going to divide this into 8 parts, right? So F is D, D, D bar, and so on. So you'll deduce that logic here, and based on that logic here, you'll give the gates here. Very very easy here. See, F was D here, directly D became what? 0, because this is the first input. 0 is the first input, right? Similarly, for the second input also D. Now third one, which is 2. What was it? D bar, so just not it. And then 0 0, you'll give 0 to 3 and 4, you'll give D to 5, and then you'll give 1 to both 6 and 7. So you have implemented a circuit easily using a mux, right? And dmux is just the reverse opposite. So dmux is based on those select lines is going to give you the output. Based on the select lines is going to give you the output. And it is just the reverse truth table. I'll just show you in that slide, one second, right? um, and it's a simple decoder only. Simple decoder only. Based on the configuration of select lines, it gives the output. Okay. So I'll just show you this. Then we'll wind up. So what happens? Combination circuit. Okay. Full adder, half subtractor, 4-bit adder, mux. Oh, you don't have multipliers. Okay. But okay, that was there in the slides. I don't know if Verma said taught, but yeah, that was there in the slides, so I taught it. No issues. Um, yeah, mux. Yeah, okay, great. Cross one. So we all just we see. Yeah, see this? 4 to 1 using 2 to 1. What they are doing, see? Overall circuit should have 4 inputs and 1 output. But in between circuits should contain 2 inputs and 1 output. So we first take two inputs and generate 1 output. Take those 2 inputs as 1 mux. So technically 2 inputs and generate 1 output. Now, because there are going to be overall 4 inputs, you have to make 2 select lines. Give one select line to these 2 muxes, give another select line to this. That's it. You can actually work out this logic, see if it works. Understand this. When select line configuration is like this, you should always do this, hard code it, right? So S0 S1 configuration 0 0. When S0 is 0, what will this output? This will output as W0. When S0 is 0, again, what will this output? This will output as W2. So W0 comes here, W2 comes here. So what will this output? This will output the one which comes to this line, which is W0. So 0 0 W0, right? Very simple logic. You will see two things coming to a max. You will see what is the select line configuration. Based on the select line configuration, if it is going to be 0, corresponding input will go as output, right? So you can reduce that for other things. I can do that for what? When S0 is 0 and S1 is 1. S0 is 0 and S1 is 1. S0 is 0, W0. W0 will come here to this position. When S1 is going to be 1, S1 is going to be 1. Okay, S0, okay. S0 is going to be 0, W2 will come this position, same thing. So W0, W2. But S1 is 1. So instead of W0, W2 will be chosen. Right? W2 will be chosen. That's all. Right? So that case should be clear. Now you can implement 16 to 1 using 4 to 1. Again, you'll what you do? 4, 4, 4, 4, you'll split it, and each 4 will generate 1, 1, 1. You will convert to you will connect them to a final one, right? And because it's a 16 one, you'll need what? Overall circuit will need how many select lines? Overall circuit will need four select lines. So, and the individual circuits are all 4 to 1 muxes. They will need two select lines each. So you'll give two select lines to the all the four muxes here, and you will give two select lines to the last one, right? So that's the thing. Demux again, the reverse logic, right? So understand this thing. Based on 0 0, the corresponding output line will turn on. Sorry. So if it is 0 0 configuration, y not will turn on. 0 on configuration, y1. 1 0 configuration, y2. 1 1 configuration, y3, and so on. Right. So simpler to understand. You can do that for this also. 1 is to 16 and so on. Decoder we have done enough, I guess. Um, yeah. So that is the thing. Same thing. 3 x 8 decoder. Okay, we have done anything, right? So yeah, again, they've done the 3 to 8 using 2 to 4. Again, what happens here? 3 to 8 decoder. So overall, it should be collecting 3 inputs and it should give you 8 outputs. But internally, 2 to 4 should be working on. So take two things, generate, and the third thing is done as what? Enable line. Enable line. We did that there, remember? So that was the thing. Yeah. So decoder, demux, encoders. So encoders we have seen. So how does encoder work? Encoder works by, again, the reverse logic of a decoder. What happens? If y naught is going to be there, y naught minterm is there, then what is the combination? 0 0 combination. Y1 0 1 configuration. Then 2 1 0 configuration, and so on. Right? So you can always build these things. And private encoders also we saw. And we deduced the logic for it and we did the KMAP also. Till this point, if you have any queries, feel free to ask me.
Hi guys, I'm Srijay and I'm going to be taking Unit 4 for y'all. So, in our case, Unit 4 is sequential logic circuits. So, let's start. So, basically, to talk about this particular unit, it's a what to say, it's a mid-level unit. So, we need it has sort of everything, right? So, it has theory and it has many problems as well. So let's go through all of them one by one. But I assure you, the problems are not that hard. Like you don't need to think as much. I mean, you don't need. There's not much problem solving involved. If you just follow the proper algorithm for all of them, the results are pretty easy to deduce, right? So let's start. So first of all, what is sequential circuits? So sequential circuit is basically the combinational circuit which has a particular memory element attached to it. So basically, uh, you know how combinational circuit works, right? So you give it an input. With the inputs it has, the proper combinational circuit will process the inputs which is given to that, and then it will provide a what to say, a consistent what to say, a discrete output for the inputs that you give. And depending on what to say, only the determination, I mean, the outputs are only determined by the processes involved inside and the inputs. There's no other factor which involves in which has the potential to alter the outputs, right? So that is combinational circuits. So now, but again, it's a very simple circuit, right? So for stuff, for systems which you need a feedback path, we use this sequential circuits. So what does sequential circuits do? So it basically also has an attached memory element associated with it, which will also influence the process which is involved to produce the output. So what as is, so in a sequential circuit, the outputs are not determined only by the inputs, but also by the, only by the given inputs, but also they are also determined by the inputs which are been given before also. So those are sequential circuits, right? So there are primarily two types of sequential circuits. We'll be talking about this a lot. So make sure you get this concept cemented in your mind. So sequential circuits are of two types: synchronous and asynchronous, right? So synchronous, the it's pretty easy to differentiate between one and another. So basically, synchronous circuits follow a same pattern across the system, right? So how to say this? They, for example, if you take a like what they follow a common clock. Um, like what to say? The analogy that I have is for this is the railway systems, right? So when you take IRCTC, so if they tell that a particular train is going to leave at this particular time, that is going to be the same across the entire India. Like it doesn't, like they don't say the time relative to some, what to say. If they say it's noon, this particular train is going to leave at noon. That is going to be the asynchronous circuits. So it's change like what to say. When you hear information, when you hear someone saying you that this particular train is going to leave at noon, that can change from person to person. Right? From the state to state, right? So that is asynchronous. Whereas in synchronous, it follows a proper time signature. Like if they say the train is going to leave at 6 p.m. exactly. So the 6 p.m. is same for everyone across India, right? So that is synchronous. So outputs can change only at specific time, and it's the time signature is common for across the system. Like there is no other what to say discrepancies among the inside the system. Whereas in asynchronous, as I said before, it can the outputs can change at any time. It's not any time. It depends on the system, the particular system. But generally, basically, what asynchronous is, it doesn't have proper time signature associated with it. A proper time interval associated with the changing of outputs, right? So that is the main type of classification in sequential circuits. And apart from that, there are also a class of sequential circuits called multivibrators. So basically, what this talks about is this talks about the number of states your circuit can go on the process of giving you the proper output, right? So they can be of three types: bistable, monostable, and astable. So I mean, it's pretty easy to differentiate. As the name suggests, bistable is just a process when you have, I mean, the output can be of only two stable possible states. Like in our case, it's 0 and 1, or it can be true or false also. And basically, it has just two stable states, one low and another one is high. So that is bistable. Next one is monostable. What happens in monostable is when you give, I mean, when you make the system to do a process, it will usually be at a stable state. So to come out of the stable state, it will go to unstable state, complete the process, and then come back to being the ideal stable state. It's that so that is monostable. Another one is astable, which doesn't have any stable states. So it's usually used in cases where you don't need any stable states, like for example in a random number generator. It's not an exact example. I'm just saying, right? So those are the types of the multivibrators which are there. So as far as our course is concerned, we don't care about the monostable and astable states. So we're gonna go ahead with bistable states only. So before moving on, I hope I'm audible and I'm clear for people, right? So if what I thought until now is clear for you all, I can just react. Okay, yeah, yeah, guys. So next, yes. So bistable states. In the bistable states, it is primary. I mean, two of the main bistable logic devices that we use are latches and flip flops. So these are going to be present throughout our chapter. I mean, these are latches and flip flops make up Unit 4. So yeah, and so yeah, that's it. Next one is yeah. So latches and flip-flops are part of the memory element, right? So before going on to it, we'll just understand what memory element is. So a memory element is a device which can remember value indefinitely or change value or command from its inputs. Right. So basically, again, I can explain it better via this characteristic table which is given right here. So can basically have a set or reset or it can be in a stable state, right? So if on Q of t, unless and until you change I mean, you give a command to change a value on its inputs, the value which is stored on the particular memory element will stay as is, right? So, for example, if you take a q of t, irrespective of the value on that it has on q of t, if you give the command for it to set the q of t plus one in the q of t plus one state, it will be set to one. And same with reset. If you reset, irrespective of the state which was on q of t, it will become zero on the next state. And if you don't change, or if you don't change anything, it will remain as is. So that is memory element. So yeah, this will be a bit confusing. I think it will be taught in the next subsequent slides also. So I'll come here directly. So yeah, we come to latches and flip flops. Okay, so basically the memory elements are classified into two parts. I mean two types based on it how it gets triggered. Like remember when I told you that these uh, like it has a particular memory element. I mean, sorry, the sequence circuit will have a particular memory element which will influence the decision of the circuit as a whole, right? So, I mean, the type of triggering is important for us to differentiate between differentiate how the trigger, I mean, how the, like, how to say, when will I mean, what, wait. So the time in which this particular memory element will influence the decision of the sequential circuit will be very important for us, right? So in that way, because of that, we divided into two types of triggering and action. I mean activation. Those are pulse triggered and edge triggered. So basically, we can see that here. So pulse triggered is this. I mean, wait, yeah. So this is pulse triggered. I mean that is a pulse and this is an edge, right? So based on this, we differentiate the two latches and flip flop. So latches is a pulse triggered memory element, whereas flip flops are a edge triggered memory element. So first, I have an nice analogy for to explain this differentiation, right? So latches are like the, I mean, let's take our the food scenario in our college, right? So what are the types of facilities that we have here for foods? So basically, we have various food stalls, and then also we have the mess for hostelers, right? So latches are like the food stalls that you go, like they, of course, they have a, what to say, like, what will you, I mean, when you have to go to buy some stuff to eat, what is the only criteria which will prevent, I mean, which will, what to say, influence a decision? The money, obviously, right? So if you have money, you will, and obviously, I mean, we have enough time, free times for us to go and eat it, right? So the only concern will be money. If you have money, you're gonna, and if you feel like it, you're gonna just go buy to, I mean, go to one of the food stalls and buy what you like, right? So that need not have a particular time interval. So if you have a free period, irrespective of the time, even if you go at 2 o'clock and go to the steps and ask for some stuff, they will give you, right. So there's no particular time which is involved. So that this can be, I mean, the food stalls in our campus is a perfect analogy for how latches work. Right. So it's pulse triggered. I mean, we can't see. I'll come back to that clarification later. So basically, latches. What to say? They don't necessarily have a particular time interval for you to work on. I mean, the time interval is not that important here. So that's what I mean, right? So latches, there's just two states, on and off, and it'll also have a particular pin called enable pin, which we'll be talking about later, right? So that's latches. For flip flops, the we saw about foot stalls and for latches, right? For flip flops, let's say, I mean, the analogy for that is the mess we go to, right? So we have a particular time interval that we are supposed to go in order to get our food from the mess, right? Like you have a particular time interval. You can't just go to, unlike food stalls, if you can't just go to uh, mess at 2 o'clock and ask for food, right? So there's a particular time interval only within which you have to go. So that's how flip flops work. So these are edge triggered flip. I mean, these are edge triggered memory elements. So only during that time you can access. I mean, what to say? You can access the facility of the flip flops, right? So there's a. I mean, edge triggered are further divided into two categories: positive edge triggered and negative edge triggered. So I mean, positive edge triggered is just like, what to say? Yeah, yeah, right. Positive edge is when you go from low to high. Yeah. When you go to low to high, you get positive edge, and when we go from high to low, we get a negative edge, right? So that's the types of edge trigger. I mean, the types inside the edge trigger flip flops. So yeah, now this I will come back to the clarification which we have. So what I have done here is latches are called pulse triggered because they can operate whenever there is a straight line in the graph. You need not necessarily have a clock wave to have ones or zeros, right? So what I mean by this is, uh, like you will get to have this doubt in the later parts of the uh, chapter. So like you will just have an enable pin which is required to make the latch work. So you can be like, how can, I mean, then what's the use of clock here, right? So they are called pulse, like, what to say? This can be a straight line. See, like, no matter the clock, uh, when latches work based on these pulses, uh, you have to be the only criteria I have in latches. It has to be in a certain stage, which is like it should be in one or zero, one or zero. So these are essentially straight lines, right? So technically, the straight line, I mean, the straight line can be as long as you want, and that's enough for latches to work, right? So that's why it's called as pulse. I mean, latches are called as pulse triggered because this technically, according to latch, the pulse. I mean, the positive pulses can be as long as it wants, as long as the pulses are there. At the positive pulse or negative pulse, it will work, right? So that's how latches work. We just assume it. I mean, we are not assuming it. We're putting it under the uh, triggering types because it makes sense. Okay, so yeah, that's a clarification I had to provide. Uh, yeah, whereas for flip flops, you need edges. The very presence of the edge makes the thing a clock wave. Like, see, yeah, this is what I wanted to say. Like, when I said for latches, it can be any long, right? The lines can be any much long. But for since flip flops require this particular, what to say, uh, this thing to work, this particular edge to work, right? So, if you look at that, a line can be as long as it wants. But when you have this sort of mechanism, this automatically becomes a wave. Okay, bad, very bad drawing skills. So, yeah. So, for latches, only this is enough. This is enough. This is enough. But for flip flops, you need this, right? So, the very presence of this edge automatically makes this a wave. Right. So that's why in the future parts of the chapter, I mean, the subsequent parts of the chapter, we will see that flip flops are the one which actually requires a clock wave, whereas for latches only enable pin is enough. So that's the reason. I'm just giving it in advance so that you don't get the doubt when we go to that part of the chapter. So yeah, we're gonna go into the different types of latches and flip flops. And before that, I hope the what I have explained until now is clear, I guess. Is it clear, guys? Yeah. Okay. Yes. Yes. So yeah, we'll go to the latches. Wait a second. Yeah. So yeah, guys, we'll go to latches. We'll start with the SR latch. So basically, there'll be various types of latches and flip flops. Uh, you'll primarily learn the latches part, and then flip flops will just have an extra addition to it, which we'll discuss in the when it actually comes, right? So first, latch. So SR latch. So SR latch, I mean SR stands for sit and reset, right? So you learn. I mean, this is basically how a latch works. This is the base. I mean, SR latch is a basic, what to say, fundamental type of latch which we could have, right? So it basically just executes the concept of latch. So it has two outputs. It has two possible outputs. Wait, where is it? Yeah, it has two possible outputs, Q and Q dash. I mean, it's basically one or zero. Uh, when the Q is high, the latch is in set state, and the Q is low, the latch is in reset state. We think about this in the opposite. I mean, in the counterintuitive way. So, where is that truth table? Yeah. So, based on the inputs of S and R, Q and Q dash will change, right? So when there's no, if neither of the pins are not activated, there will be no change. And when set is made high, irrespective of the state of pass, pass, the process will prefer Q over Q dash, right? And then similarly, when reset pin is activated, the process will prefer Q dash. And yeah, this is where things get a bit uh, confusing in SR latch. So we told that like what is it? I keep losing the track of this pen. Yeah. So let's say this. Okay. Like what? Yeah. So process is occurring. You're given input, uh, and if S is activated, I mean wait, if S is activated, it prefers Q, and when R is activated, it prefers Q dash. So the question arises, that is, what happens when both of them are activated at the same time? So the system will have a confusion on whether to go to Q or Q dash, right? So this is a disadvantage that we have in SR latch. Uh, yeah. So we'll there's obviously a solution for this. I will come to it later, and yeah, we'll go here. Yeah, guys. So this is an additional specification. Uh, Usually primarily we use active I input SR latch. So basically it's just it gets active when the input is high, right? So that when the only when the input is high and the it is in a when edge trigger. I mean, if an edge trigger is happening, only under those two conditions will the this particular latch work. This is what we will be discussing for most of our lectures wherever SR latch is mentioned. So again, this active I input active input SR latch is also called as NOR gate latch because in the for the implementation of this latch you will require NOR gate. So yeah, this is okay, same stuff. Yeah, um, yeah, we'll come back to it. We'll come to this. Okay, so yeah, uh, this is just how the implementation of latches. So it's I don't know whether it's important or not, but it's just preferred to learn this. Like this makes your decision making process and I mean your problem solving better if you understand what is actually inside all this SR latch and then latches in general. It will help you better in solving problems in the future. I mean, when the problems, I mean, when the questions come, right? So yeah, as I said before, it's an OR gate. You have basically set and reset. You have basically set and reset, and put both of them in an NOR gate, and then when you give it as an output, and then you give the output itself to the as one of the inputs in the NOR gate, right? And wait, yeah. So Q's input is also given as one of the, I mean, see, Q is also given as one of the inputs in S, and Q bar is also given as one of the inputs in R, right? So this influences the, uh, what to say, the decision making process in a system, right? So yeah, I think this is the starting stage when there's nothing involved. I mean, the start of the process when set pin is activated, obviously it prefers obviously it prefers Q or Q dash, so 1 0, and then when nothing happens, it remains in 1 0, and then a reset pin is it prefers Q dash, so and then again no change, it remains in Q dash. Now when both set and reset pins are activated, it goes to an invalid state, right? So this is what SR latch is all about. So in order to add an additional, what to say, uh, an additional verification, once it's a verification process, what to say, just to make sure things don't go haywire that easily, we have this particular thing called gated SR latch. So what it does is it just adds an extra enable pin to it so that the system will, like, what to say, the functioning of this system is under all control. Like only when we give the enable pin to be one, only then will the latch work. So we have the power in our hands in gated SR latch. So yeah, it's pretty simple apart from this starting to explain. So when enable pin is zero, irrespective of whatever is in both of them, nothing will happen. And when enable pin is set to one, when this nothing, yeah, latch, yeah, rest of the things are same. And only when you get in the enable pin also, there's a possibility of all three being high, which will lead to an invalid state, right? So yeah, yeah, yes. So this this is why latch circuits are not suitable in synchronous logic circuits because obviously, uh, it's pretty obvious, I guess. And I mean, they have given a very nice explanation for this. When the enable signal is active, the excitation inputs are gated directly to output Q. Thus, any change in the excitation input immediately causes a change in the latch output. So yeah, if it is not clear, I can explain it better. No, yeah, I will come here. So take this right. So in this SR latch, when the enable pin is active, so uh, S is given, R is given, right? So when the enable pin is turned on, I mean, what to say, the changes that we give in the input are immediately reflected in the output. Right? If you see here, when you change it, I mean, what to say? Yeah, if you take this, wait, my God, so, yeah, when it's enabled, see, when it's 0, 0, there's nothing happening. And when you change the reset, I mean, when it's set the reset pin to I, the change is observed almost immediately. In the same time, I mean, it's almost real time change which is happening, right? So there is this volatility which is involved in the latch circuit. So which makes it unsuitable in cases where we have want to know that. I mean, we have to have this latch circuit become sort of unpredictable after time, and these are not suitable for cases where we need to know. I mean, where we need to have a control over the time in which the inputs are changed. I mean, the inputs and subsequent outputs are changed, right? So yeah, and then wait. So how do you solve this? How do you solve this problem of immediate change in thing? That's where flip flops come in. So what it does is it gives this latch a particular time interval. I mean, sorry, it's a clock wave. I mean, clock square wave, and it restricts the time in which the states of memory of a memory elements can change. Restrict the system to only change during the time when we require it to change, right? And it becomes predictable also. Like obviously, it's a square wave. What do you expect? And it can only, I mean, the changes can only occur at either positive edge or negative edge, right? So this is what leads us to memory elements, edge trigger memory elements called flip flops. So yeah, I hope this transition between latches and flip flops are okay for you all. Can you guys reply? Yeah. Yes, guys. Yes. So yeah. Yeah. Next, X triggered flip flops. So what are these? These are synchronous bistable devices. Obviously, uh, output changes states at specified point on a triggering input called the clock. Change state either at positive edge or the negative edge. So I think I've explained everything about flip flops in the latches itself. So yeah, I'll just reiterate the points again. So flip flops can only, I mean, changes its input. I mean, I mean, constricts the time in which I can process the information only to these edges, right? I mean, sorry, wait, what? Yeah, sorry, yeah. So yeah, a flip flop restricts the uh, process time only to the positive edges or the negative edges, right? So this makes it much more predictable and controllable, right? And it's much more stable as well because you follow particular consistent time clock uh, stuff, which make it more consistent. So yeah, uh, when it comes to SR flip flops, yeah. So I have a very nice analogy to explain this flip flop, this transition between latches and flip flops. So let's say I'll come to that. Okay. So SR flip flops on the triggering edge of the triggering is basically the positive edge. Okay, positive edge of the clock pulse. When SSI and this rest of the stuff are pretty easy. When SSI and R is low, it's in set stage. When R is in high and S is in low, it goes to the reset stage. And when there's no inputs are in when no none of the inputs are high, no change. And when both inputs are high, it goes to invalid condition, right? So basically what we do is we introduce a clock. So yeah, I now come to the analogy. So when we see in movies where let's say what to say, yeah, take Shivaji movie for example. So there is a stage. I mean, when Shivaji goes to a point where he has to give to a bribe to officials. Uh, do you remember how the process will happen? So basically, what happens is Shivaji will be ready to give bribe. He will first go to an assistant, which who will inform the main official that okay, this person is actually ready to give bribe. So after the person communicates with it, and then the official tells him the amount that he has to the Shivaji has to give as bribe, and then it comes back. I mean, and then the assistant comes back to Shivaji, and then the process occurs, right? So you can take this analogy and in nicely explain flip flops with it, right? So in our case, the clock acts as the bribe. Okay. So what happens? Obviously, what I will say, only when the bribe is given, they will tell that they'll do whatever Shivaji says, right? So that's essentially how clock works. Clock works at flip flops. Only when the clock is at a particular position which they want, the system will do whatever it says. I have accepted, like say here it's positive. I mean, it's positive edge. So when the clock is at any stage apart from the positive edge, no change will occur. Like it can be like this, it can be like this, it can be like this. No one cares as long as the clock. Only when the clock is in the state where they decided, uh, all this stuff happens, right? So here clocks, a clock can be taken analogous to the bribe which is given. Only when it is given, stuff gets given, right? So yeah, and then so yeah, more adding on to it, SR flip-flop basically comprises of three parts: basic NAND latch, a pulse steering circuit, and the pulse transition detector. So yeah, the pulse transition detector. When coming back to analogy, here the pulse transition detector acts as the assistant who says, you know, okay, this person is ready to give the bribe. Tell me the amount, and you see this conversation happening between the Shivaji and the official, right? So yeah, the pulse transition detector acts as the assistant in that analogy, right? So this pulse transition detector, PDD, I'll say it's very tough to pronounce the entire stuff. So PDD detects the rising or falling edge and produces a very short duration spike. And only during that short duration spike will the entire stuff happen for the flip flops, right? And yeah, I hope the analogy is clear. And yeah. So pulse transition detector. This is the pulse transition detector. We're basically adding extra steps to make the entire stuff more stable. That's what we're basically doing. When you remember latches, it was even when the bare SR latch is the most volatile possible latch possible, volatile latch possible. Then so you added an extra latch enable pin to it, and then you are not enough, and you are not satisfied with it, and then you are adding extra clock to it, and that's what results in this circuit that you see here, right? So yeah, we have a clock. When the transition pulse transition is detected, this gets active, and then when this gets active, only when the entire thing here will get will start operating, right? So that's what pulse trans. I mean, that's what that's how XR flip flop works. So how does inside this pulse transition detector, what happens is this, right? So at particular interval, so let's see here. Okay. So when clock, I mean, let's say C and C dash. Okay. Obviously C, when C goes in this way, C dash will obviously go in the opposite way. So when only when there's a common point, the only point where both of them will be come to the same agreement is the uh, edges, obviously, right? So in our case, I mean, we usually operate the seed as at some time interval again. I won't say again. I don't know whether to say it, either again or beginning of C. So that only during the time where that edges are present will the detector produces a spike. So this is how it makes the entire flip flops. Uh, what to say? This is what makes the flip flop work. Okay, so this only during this particular interval, that is you see here, right? Only during this particular interval will the spin yeah, only during this particular intervals where the spin will be set to one, set to y, and this stuff is same as what we saw before. So this is how SR flip flop works, and I hope it is clear. Okay, sorry, I didn't see the message. So yeah, will SR flip flop only work at uh, maybe past? Not necessarily, but what to say? Um, it's preferred to work at positive edge, right? So it's just a matter of preference. So just follow same since we follow the same template throughout the chapter, we just take this as a fact that ASR flip flop will work at positive edge. But in actual industry, it's not the case, not necessarily the case. But that depends on the actual flip flop manufacturer, and it's their wish. Depends on what their preferences. Okay, which slide should I repeat? Can you mention the one which is actually on right now, right? Okay, yeah. So wait, it is not that. I mean, from the exam point of view, it's not important. Okay, so don't worry. But I will explain. Okay, no issues. Where is it? Why is this not working? Yeah. So yeah, welcome to first, right? So first, so to make this understand better, we'll just actually start with. Oh my God, we'll actually start with this thing right here. Okay. So this is the basically see this is the magnification of uh, the thing that you see here. Okay. Uh, okay. So I hope that's that's understood. So inside that pulse transistor detector, this is what the circuit will look like. Clock C and C dash. For ease of communication, I'm going to consider this as C and this as C dash. And this has the final C star. Okay, C star is the final output from here, and this is C star is what's going to come out of here. Okay, so when clock is given, when you look at it, for C dash we have a not gate, right? So this not gate is, if you notice, it's a bit after. It's not necessarily in the you know same place as how the C is going. Okay, see basically let's say this is the actual original C. Okay, so this is the positive C which is going inside the AND gate, which is used for the AND gate. And this is, if you notice, the NOT pin is placed after the point where this C is, the actual C is taken, right? So obviously, what it's gonna do? It's gonna delay the NOT process. I mean, what is it? The complementation process of the wave, right? So this will result in. Oh my God, yeah. So this is what you. This is reflected here. Okay, I think I should have. Yeah, I think. Oh, I hope this is better now. Explain now. So see, this is what comes here. Okay, and this is what comes here. Okay. So since the NOT gate is placed a bit later, uh, in the non, I mean, the NOT gate is placed a bit after. The you notice that there is this small delay. Okay, so the gate will obviously the gate will obviously be active only during the time, only during this particular time, right? Because see, for AND gate, obviously both should be one. Both this and this should be one. Only at that time this can be one. Otherwise, it's going to be zero, right? So when is both the C and C dash one, only during this particular very small interval that you see right here. Here, yeah, here. Okay. Only during this very small interval that you see right here, both of them are becoming one, and that's when this AND gate becomes one. Right. So this is what gives this very short duration spike that you see. The that enables the pulse transition detector to enable the entire process on the particular time interval that you want. Okay. So yeah, this is for the rising edge, and same is the case for the falling edge. So you just add an extra not gate. I mean, I won't say it's a not gate. I don't know how to explain it. You basically just complement it back. Okay, you're basically just recomplementing it this back, recomplementing this. Okay, what to say? This is original C. This is yeah after C and the C which we take for consideration. And then we give the this is what C dash happens. So obviously, so here both of them gets complemented again. So That is what causes the obviously since it's falling edge, this not uh, component right here will make it have common points only during place where you see what to say, only during falling edge of the clock waves, right? Only during this particular time interval both of them are at zero. After the point I mean c dash becomes 1, right? So this is when the negative only this is that's why it's called falling edge. Only during this time will this particular thing be 1. Okay, so yeah, this is actually a very niche topic. It's never been asked as of now. Okay, I don't know. If they happen to ask this in exam, you are in luck because yeah, they didn't actually explain it this clearly. So yeah, I hope so it's clear. Okay, so yeah, guys, moving on to get a delatch. Wait, yeah, moving on to get a delatch. So yeah, basically what you do is get a delatch is basically to get a delatch is the result of the when I mean it's the solution for the problem that made SR latch undesirable, which is the invalid condition. Okay, so when both S and R are set to I, what will it do? So gated delatch takes care of that. What it does? Simple. It makes R input equal to S dash. Okay. So what happens here is when it's 0 0, I mean S and S dash. Okay. S and S dash Q Q dash. No change, no change. If this is set, see, when S dash is 1, S should obviously be 0. And when S dash is okay, okay, I'm explaining the opposite way. So when S is 0, S dash should obviously be 1. And when S, oh my god, and when S is 1, S dash will obviously be 0. So there is no case where this could be 1 and 1. No, this is not possible here. Obviously, because it's a complement. Okay. So this eliminates the undesirable condition of having an invalid state in the SR latch. So yeah, it's pretty simple apart from this. You just have a same input point. You give the actual one D here. You give D dash here so that and the rest of the stuff is same, right? So that's what makes the get a D latch. Yeah. So yeah, only yeah, D size latch is set and when D is low, latch is reset. Yeah, it follows. Yeah, and also D is also I mean the D in latch get a D latch stands for data. Okay. You only have only since the only a single input stream, it's called as data input. Right. So yeah, when enable is one, enable should be 1 year as well. Okay. So when enable is one, and D is zero, it's in the reset, and when D is one, it's in reset. See, when D is one, it's in set. Okay. When enable pin is zero, irrespective of the state of D, it's there's no change occurring. Okay. So yeah, when D flip flop is just you add an extra clock to it. Okay, yeah. You just add an extra clock to it to make sure. Yeah, clock is the bribe. I told you. Okay, so only when it is in the rising, what is the rising edge, will the stuff be happening? Okay, so yeah, that is D as far as D latch and D flip flop is concerned. It's pretty simple. Um, yeah, any doubts? Okay. Do you guys have any doubts as far as the D latch is concerned? It's fine, right? Okay. Can you tell? Okay. Oh, no doubts, sir. Okay, sorry. Yeah. Let's move on. Okay. So next, JK flip flop. So this is where it gets interesting here. Okay. So what it does is, see, like SR latch. I mean SR. I mean sorry. SR basic SR flip flop has this particular negativity association. disadvantage associated with it, right? Which is the invalid state. So D flip flop provides a solution, and JK flip flop provides another solution. So you saw D flip flop was a much more simpler approach. In JK flip flop, what we do is the Q and Q dash are fed back into the actual NAND gates itself. So what happens is when both are set to I, it will reach a toggle state. Toggle in the sense one at equal intervals at one edge. I mean equal intervals when the clock associates the rising edge. Q will be preferred, and I mean what to say. On one rising edge, Q will be preferred, and the next rising edge, Q dash will be preferred. So it goes to this toggling state, right? So that's how JK flip flop takes care of the invalid condition. So yeah, yeah. So you see here, uh, rest of the stuff is same. What you do is, yeah. Uh, 1 second, guys. 1 second. So yes. So where was I? Yeah. So let's assume, let's take the case where where did I leave this? Okay, see, other stuff is same, literally the same. Okay, 0 0 na no change, 0 1 na reset, 1 0 na set. So rest of the stuff is same. Let's come to this particular condition. Okay, so let us see. Oh my god, I keep losing this track of this pen. Okay, so yeah, 1 1. Okay, so what happens here is obviously you give here 1, you give here 1. Uh, let's assume this obviously the clock is enabled right now, so that is also 1 as well. So let's not talk about this for now. Okay, so obviously since this becomes 0, like okay, 0, and then this becomes NOR gate, so it's complemented, so this becomes 1, so this becomes 1. I mean, not for now. I mean, let's just assume it becomes now 1 for now. Okay. So what happens is this, what, I mean, same year. Okay. So it's 1, it becomes 1 year. So it becomes 0 year. And it becomes, so obviously, since because it was not component, it becomes 1 year and becomes 1 year. And yeah, this is the case. Okay. What happens here is the queue is connected to the this particular pin. Okay. So what happens is 1 1, so it becomes 0. So what to say? Wait, am I missing something? Yeah, yeah, yes, fine. I'm sorry for confusing. So what happens here is the queue will also influence the decision making of this particular AND gate. So that what happens is at one point of time, this will be, I mean, Q will become 1 and Q dash will become 0. Like the confusion is because we didn't consider for this particular uh, this thing early on. Okay, so that's why there was some confusion. Don't worry. Let us assume that there's this there's this process going on. So how that will happen is at one edge Q will be preferred and another edge Q dash will be preferred. Okay, so there is this constant toggling between the preferred states. So this is what happens. So irrespective, like see, uh, yeah, wait, yeah. That's why it's Q here. Okay, so when the invalid state is attained, the Q gets activated. The toggle Q is the toggle state here. Okay, so irrespective of what's given here, they keep switching. I mean, it's not irrespective. Okay, sorry. I mean, what happens here is so when it's 1, it becomes 1. Okay, so since reset pin is activated the first state, it becomes 0. Then set pin is activated, so it becomes 1. So this process keeps on occurring for as long as we want it to. Okay. So this is how JK flip flop works. Okay. So basically, JK flip flop is a bit more abstract. So, like how to say, there's no proper way to explain JK flip flop. It's not as easy to, I mean, it's not easy to chain down JK flip flop into words as D flip flop is. So you just have to take my word. So what happens? JK flip flop is also known as toggle flip flop. Okay, so what happens is when both the J and K is set to 1, flip flop goes into toggle state where in the alternative position Q and Q dash are preferred, right? So there's this equation which is given for toggle flip flop, that is J dot Q dash. Okay, sorry, I mean, yeah, it's given. Okay, so it's J dot Q dash plus K dash dot Q. So is this equation important? Um, Sort of. Okay, there may be questions, 1 mark or 2 mark questions, which may be asked based on this formula. So they may give a case study where they will ask you to figure out the qt plus 1 state based on uh, the given based on the already given state, right? In the using this JK flip flop. So during those cases, this formula is important. I mean, this forms obviously this formula is required. You can't just. I mean, you can put the flip flop. I mean, you can write down the table, but this formula makes your life easier. So I'm not. I mean, it's not very frequently asked question, but if they happen to ask, you just have this thing in handy. Okay. So yeah, is there any JK flip flop extra stuff? Yeah. So is the JK flip flop part clear? I know JK flip flop is a bit abstract, so just it's easier to just take my word as is. Like if you want to, you can obviously ponder upon JK flip flop more. But since there's a particular time crunch, I can't explain it bit too much, right? So yeah, I hope JK flip flop is clear. Next one, characteristic table. Uh, yeah, so T flip flop. So T flip flop is basically how D flip flop. It's basically D flip flop, but for JK. Okay. I mean, well, I mean, okay, never mind. Basically, it's just a single input version of JK flip flop. You just tidy both inputs together, and the rest of the stuff is same. And in the equation also, instead of having J and K, you just have T at both sides of the both parts of the equation, right? So yeah, that's that. There's nothing much here. Yeah. So this is that. This is a very simple stuff. This is just a thing to note. Okay. So SR, D, and JK edge trigger flip flops have this, like when you represent these flip flops in diagrams, you need to obviously mention a clock, right? So for clock, you have this particular symbol right here, which is okay. So you have to represent it using this greater than symbol. I mean, it's not greater than symbol, it's an arrow symbol. Okay. So when it is positive edge triggered flip flop, you just put this, and when it's a negative edge triggered flip flop, you just do this. Okay. So yeah, guys, this is the this is just a thing to note. Okay. So yeah, flip flops. With this, we sort of complete the concepts related to directly related to flip flops. Uh, this flip flop is, I mean, this part is actually very important for everything. Okay, for both exams as well as when you actually want to study more on this, it's pretty important, and it's very important to differentiate between each of the flip flops. That see, when you take it at a surface level, surface value, these flip flops might be very easy to, like when you study, it will feel very easy. Okay, this is just this. This is JK flip flop. This is D flip flop. But when you actually try researching more on this, you will realize that it is very confusing. Okay, when you take actual case studies, that's when you'll feel very confused on which sort of flip flop is this, which sort of flip flop is that, right? So, of course, when you have time, just go through this more research on this, ponder upon this. Okay, so yeah, we move to counters. Okay. I mean, the definition you're given for counters here is pretty nice. Okay. So basically, counters are circuits that cycle through a specified number of states. So it's just basically counting mechanism. Okay. You count through it just like how you count through seconds in a clock. Yeah, there it's clock. Here, and as far as counters, this generally refers to states. Okay, any state. Okay, we mentioned the states which is required for it to count. Based on it, it will either count up or count down. Okay, so yeah, just like in memory elements, counters are of two types: synchronous and asynchronous. Synchronous are called as parallel counters, and asynchronous are called as ripple counters. Okay, yeah, these 2 points will be discussing in much more detail in the next subsequent pages. Okay, so one second, guys. So yeah, asynchronous counters. Asynchronous counters are also called as ripple counters. So these are the counters which do not stay in states at exactly the same interval. Uh, Obviously, because they do not have a common clock wave associated, which will make the entire process consistent. So they are also called as ripple counters because the mechanism of this particular asynchronous counter involves the ripple effect. Okay. Yeah. Actually, the definition here would be pretty nice. Okay. It is also known as it is also known as ripple counters because the input clock pulse ripples to the counter. Uh, yeah. The drawback is the cumulative delay. Yeah. I will mention about this when I discuss along with the diagram. Okay. So yeah, this is a very important point. When you have, we can actually take this the other way around also. So using n flip flop, you can make a counter with of value mod 2 power n. Okay. So basically, what it means is you basically have the this particular. I mean, sorry. Where is it? Where is it? Where is it? Yeah. So yeah, this is mentioned here. So a mod X counter cycles through X states, right? So I know that we mentioned the number of states which the counter has to go, right? So mod 5 counter will go through 5 states before coming back. Mod 10 through 10 states, so on and so forth. Okay, well, those are bad examples, like what to say. Mod 4, mod 8, mod 16. These counters go through the states which they have in the mod dash. Okay, so how it acts as is when there's n flip flops involved, you can make a mod of 2 per n counter. Okay, because it uh, obviously you go through. Okay, I mean, I think I could explain it better in the later part of the chapter. Okay, yeah. I'll explain it better in the subsequent pages. Yeah. So the output of the last flip flop, MSB, divides this is just a common trivia. There's nothing to explain. Okay. So the output of the MSB will divide the input clock frequency by the mod number of counters. So hence a counter is also called a frequency divider. So obviously, if there is let's say 8 states, so the time taken by the counter to go through all the 8 states from 1, 2, 3, 4, 5 to 8 will be obviously 8 times. Okay, 8 times it takes to go through a single state, right? So if it takes, let's say, if the t is the time taken by a flip flop to go through one count, okay, then obviously it's gonna take 80 for going through 8 states. I mean, oh my god, it's gonna take 80 for to go through all these states. So t time. What is 1 by time frequency? So 1 by 88, I keep missing this. Yeah, 1 by 80 is 8f obviously. So you notice that how this works. Okay. So see, wait, what? F by 8, sorry. Yeah, say F by 8. Uh, yeah, you see how this mechanism works. So that's why counters also called as frequency divider. Okay, this is just a small trivia. You need not understand it that well. Okay, so yeah, yeah. To explain this asynchronous counter, I have this example, a 2-bit ripple binary counter. So what happens is one of the output of one flip flop is connected to the clock input of the next more significant flip flop. So you see what happens here. The output of uh, the less significant flip flop is one of the inputs, is the clock, which determines when the more significant flip flop to should occur. I mean should work. Okay, so I can explain this better. So basically, uh, where is the yeah? So I mean this can be here as well, and this can be here as well. So okay, so oh my god, yeah. So the functioning of this flip flop depends on when the output of this flip flop occurs, right? So we see clock here, so it can be sort of misnomer. So what it means here is this flip flop will start to work only when there is a credible output for the previous flip flop. So that's what it means. So that's why the functioning of this counter is ripples through the flip flops which are involved. Okay, so that's what happens. So this is pretty this the best way we can represent it is using the timing diagram you see right here. So for each time interval, you get 1, 2, 3, 4. For increase, you see how this works, right? So yeah, yes. So this is how asynchronous ripple counter works, and this is also another example. This is just a more complex example, and yeah. So when they required, yeah, how much states will, so yeah, what state will mean, what counter will it be? So since it's 2-bit counter, it will be 2 power 2, uh, mod 2 power 2, which is mod 4 counter. This is a mod 4 counter. And next one is since it's 2 power 3, wait, it's a mod 2 power 3 counter, therefore it's mod. Wait, to the yeah, it's a mod 8 counter. Okay, so basically that's how this works. Okay, so is there any example for this? Any other example for this? No. Yeah. So this is the basic functioning of an asynchronous stuff. So I hope this is clear. Is it clear, guys? Okay. Yeah. So yes. So you might have noticed a particular uh, problem which is in this particular thing, right? So you see, you can only represent mod 2 power n counters, right? So they can either be mod 2 or mod 4 or mod 8 or mod 16, right? Can only be in 2 power n counters which are possible. I mean, mod 2 power n counters possible, right? So you might ask, only can we only function within these particular counters? The answer is absolutely not. Yeah, this is where the gates come into play to make your life better here. Okay, so yeah. So for asynchronous counter, mod number less than 2 power n, we use gates, not gates, I mean, sorry, see, I mean, NAND gate, which will result in a truncated sequence. Okay. So what you do is, let's say, okay, what is this? 2 power 8, right? So, 8, yeah. So this is actually a mod 8 counter. So what we do is, let's say we want to stop it at a particular interval. Okay. So what is it? So 0, I mean, okay, wait. This is 1, 10, 100. Okay. So what I do is, they only when, wait. Um, so this is the least significant bit. So this is the least significant bit. Second, ones, tens, hundreds. So one is left as it. When okay, yeah. So yeah, guys. So when how should I say this? Okay, so you see the interval. I mean, the time as the time moves on. I mean, as the count goes on, the flip flops keeps increasing their values one by one, right? So what happens here is, you see that they are given, they have connected this NAND gate to B and C. Okay. So what happens is, when this it's the stage where, like, how will this flip flop work? Okay, let's go that way. So it's 0 0 0 1 0 1 0 0 1 0. Okay, it's getting clumsy. Okay, so 0 0 0 0 0 1 0 0 1 0 will go through all these states until a point zone 1 0. Why? Because obviously it's pretty simple. Okay, so C is connected to this gate and B is connected to this gate. So obviously, when it's 1 1 0, this pin gets activated to 1, and this will clear the entire sequence, and the entire sequence will start from first. So what is 1 1 0? Wait, I forgot. 1 2 4. So 4 plus 2 6. Yeah. So this sequence stops at 6. Wait, what? Yeah, 6. Yeah, sorry. Yeah. So it's 6. At count 6, this gets cleared, and then the process repeats again. Right. So I mean, I'm not okay. I'm not able to process the binary sequence now, but you get the concept behind it. Yeah. So when you can just add the point where you want the sequence to get truncated, you add those bits. I mean, you make those bits get connected to AND gate and NAND gate. I mean, NAND gate, and then you make it connected to a clear pin, and you get yourself a truncated asynchronous counter. Okay, so okay. I mean, sorry. Wow. Yeah. Okay, they explained it better here. I didn't see this. Okay. So yeah, guys. So it's 0 1 1. Okay, so I mean sorry, 1 1 0. So it is 6. So when this sequence it's 1 1 0, NAND gate is activated, which clears the entire stuff, and the entire process starts from once again. So when you see clock goes from 1 2 3 4 5 6, the sequence gets increased one by one. And when the clock hits 6, everything clears back, and you start the process again. So this is a mod 6 counter. Okay. So this is state diagram. Okay, so this state diagram is pretty important. Okay, I mean it's very easy to draw, but it's pretty important. You might uh, need. I mean, you may be asked to draw this diagram in your exam paper. So, I mean, there's nothing to explain about state diagram, but just remember. Okay, yeah. So you get 0 0 1. This is what I mentioned. Okay, when it goes from 1 0 1 0 1 to 1 1 0, it becomes a temporary state because that's when the NAND gate gets activated and clears, and it starts from first. It doesn't go to 1 1 1. Okay, so this is how this works. Okay, so yeah, we come to the first point of problem solving in this entire chapter. Okay, so how to construct a asynchronous modify counter. So guys, I'll just give you an algorithm. What you do is for how do you construct a modified counter? So I mean mod less than 2 power n counter. So how that works is you find the nearest, I mean you find the smallest uh, 2 power n value which is near to the required value. Okay. So okay, I'll better explain it with an example. Okay. We have a modify counter here, right? Okay. We have a modify counter here, right? So what is the closest thing possible? Closest small, I mean, sorry, what a smallest possible number greater than 5. Uh, so you get 1, you get 2, you get 4, you get 8, right? So 8 is the smallest possible value which is greater than the given required value, right? So what you do is you take the mod 8 counter and you truncate it at the point where it's 5. Okay. So obviously at that point it becomes a mod 5 counter. Okay. So yeah, the same goes for mod 7. Mod 7 also, since it's less than 8, you can easily go ahead with mod 8 counter and then truncate it. For mod 12 counter, again, the next thing, 8, 16. So you can use a mod 16 counter and you can just truncate the sequence at 12. Okay. So this is that. Next is the following is what mod counter. Uh, just take a look at it. Uh, one First, look at the number of flip flops you have. So 1, 2, 3, 4, 6 flip flops you have. So it's obviously uh, 2 power 6, which is wait, 32. Uh, 2 power 0, 2 power 1. 2 power 1 is 128. Okay, yeah. 128. So this is the maximum possible here is 128. And then you see where are the NAND pins connected when C is 1 E for clear to work, you need C to be 1, D to be 1, E to be 1, and F to be 1. Everything should be 1. So, which is basically the last state gets skipped. So, it goes through 127 states and the 128 state is truncated yearly. So, this is a mod 127 counter. Okay. So, okay, they haven't given solution. But yeah, that is the answer. Okay, guys. So, yeah. So this is a decade counter. Decade counter is a type of mod less than 2 power n counter. It's also called as BCD counters. It's basically counters with 10 states in their sequence. And these are commonly used in daily life. And yeah, guys, when you are asked to design an asynchronous decade counter, you know what to do. You just go ahead with this. What to say? I think it should be 1010. I don't know. Okay. So when it hits 10, it basically should get reset to 0. That's what it is. Okay. So yeah, asynchronous. This is an asynchronous taken counter. And yeah. Mm, I hope it is clear within. Okay, sorry. I'm sorry. I didn't see. I didn't see the message. Wait. Uh, can you tell which page number your question is mentioning about? I'm sorry. I didn't see the message. Wait, yeah. Is it possible to mm, clock signals? Okay, wait. It is I want before that I'll see whether there's a way to make this pop up. Hmm, okay, damn. Okay, here is the message. Clock signals. Okay, okay. I forgot the title name. Uh, could you be a bit more specific? Uh, like, do you remember how many pages before that happened in cube or the diagram? Like, do you mean this? Yeah. So do we, we need, yeah, we need, obviously. So see, the thing is, there'll be a bit confusion. They would have just given it as Q dash will be connected here. So this can be Q also. Okay. So basic thing is, the concept is the output of the least significant flip flop will be connected to the clock of the more significant flip flop. That's the case. Okay. So here you obviously need both Q and Q dash Q bar here to make your stuff work. Okay. So there, I mean, the difference between Q and Q bar will be explained in a while. Okay. I mean, it will automatically get explained in a while. Okay. Is it fine? Okay, yeah, fine. Mm, there was a, yeah, down counters. So you saw the up counters, right? So I mean, it's basically explain. It gets your question gets explained here itself. Okay. So up counters are obviously it goes up the transition states. I mean, it goes up the states which are required. Down counters go down the states which are required. Okay, it goes from maximum value to zero. So how do you differentiate between up counter and down counter? And when it comes to up counter, Q, there is less significant flip flops. Q is connected to the clock of the more significant flip flop. Okay. Whereas in down, the Q bar is connected. Okay. So that the when you go through the clock, it will reduce down instead of going up. Right. So actually, like you had a doubt, right? Where was it? Yeah. So this is actually down counter. Okay. So that's why I know it will be a bit confusing. When I read these slides also I figured it out. So yeah, this is basically a down counter. Okay, so don't assume that this is an up counter. This is actually a down counter. So if it has to be an up counter, it will get connected. I mean the C will be connected to the Q bar. I mean C, sorry. I mean the C will be connected to Q, not okay, not Q bar, not okay. I hope your doubt is clear now. So depending on the type of counter you have, I mean, obviously you need to show both the Q and Q bar in your paper, okay? Because I mean that's how flip flop works. Flip flop should have both Q and Q bar. If not, that's not a flip flop. Okay. Why do we represent the states with Q? I mean, I don't get your question. The Q is an output, okay? I mean, Q and Q bar are the outputs, okay? So with depending on the state, okay, wait, one, 001. Yeah, because see, okay, okay, I get where you. Okay, so see here, you see in this diagram, they would have mentioned Q bar just for courtesy in this particular. I mean, sorry, wait, what? What? Okay, yeah, okay. I see where you got confused. Okay, this is a small error. Okay, so actually here, since the diagram is a down counter, they should technically care only about this and this. Okay, so instead they cared about they took this. I mean, see, I mean what I'm trying to say is this is a oh my god, this is a down counter. Okay, but this is a time signature for up counter. Okay, so please don't get confused. Thank you. Okay, so this is a bit of a discrepancy. So technically, you should only care about uh, Q bar here if it is down counter. If not, I mean this is correct for an up counter, but not for a down counter. Okay. Okay. Yeah. Thank you. Welcome. Welcome. So where was I? Where was I? Oh my God. Yeah. So this is a difference between up and down counter. Okay. So basically, yeah, this is a 3-bit binary. Mm, 2 power 3 is 8 mod 8 down counter. So this is how it works. So there's nothing to explain here. So yeah, cascading asynchronous counter. So in certain places where like let's talk about industry for for this case. Okay, so for one or two counters, let's say you need a mod 32 counter. Okay, uh, I mean you have to understand that these are these are not just not concepts and abstract entities which are needing to study. Okay, these flip flops are actually being made. These flip flop makes your laptop possible. These flip flop makes my laptop possible. Okay, so yeah, these flip flops make anything possible, and these need to be fabricated at very large quantities. Okay, so let's say you need a mod 32 counter. Okay, not even 32. Let's say you need uh, yeah, well, okay, let's take, since it's given here, I will take a mod 32 counter. Okay, let's say you need to fabricate 10 million mod 32 ripple counters. Okay, so what happens here is when you take one 10 million mod 32 ripple counters, then you get a message saying that they don't actually need 10 million. I mean, okay, yeah, 10 million mod 32 ripple counters. They only need five. So what happens here is the rest 5 million mod 32 ripple counters go down the drain. They're waste. They don't. I mean, it's worth nothing now. It's a waste of effort, right? So during for those cases, what we do is what they do is they make smaller two or three smaller ripple counters, and then they cascade it. They connect the, okay, yeah, for this I can go to definition. It will be much more clearer. So okay, wait a minute. Mm, yeah, so the last stage output of one counter is connected to the clock input of the next counter. Okay. So basically, this signifies that the both of them are connected. So what happens now when you use cascading asynchronous counters? Uh, let's say you made mod 32, 10 million mod 32 ripple counters uh, based on this, based on I mean, by cascading 10 million mod 4 counter and 10 million mod 8 counter together. Okay. So now they cancel your order for 5 million mod counters, right? Mod 32 counters, right? So what you can do, you can make this I mean, you can, now you have 5 million mod 4 counters and 5 million mod 8 counters, which can actually be of use. Okay. There are higher chances of you requiring a mod 4 counter, mod 8 counter than a mod 32 counter again. Okay. I mean, there are higher chances of you requiring a 5 million mod 4 counter and 5 million mod 8 counter, much more than a requirement for 5 million mod 32 triple counters, right? So this is for to that's the ideology behind the cascading asynchronous counters. You cascade small counters to produce bigger counters, so that these act as a building blocks. Okay, so they make your life easier when it comes to fabricating. Okay, so this is what cascading asynchronous counters is about. Yeah, guys. So this is a six example is a 6-bit binary counter constructed from two 3 bits counters, right? So yeah, the functionality of this is same as the 6-bit. The functionality of this cascaded two 3-bit counters is no different from one single 6-bit binary counter, right? So basically, this cascading effort makes our life much easier. Um, So yeah. Yeah, so cascading asynchronous, obviously. So when there is not binary counter, it requires additional output as well. You give a frequency to it. In this case, a mod 100 counter using two decade counters. So what you do is this is basically multiplication, right? So what you do is you divide a frequency by 10 and give it as a counter on as TC. Okay, this is also involved in the input of the second what to say to yeah, this is involved in the second part as well. Okay, yeah, so there's not much to explain in this, but yeah, basically when it's the counter you have to do is not a binary counter. You basically add additional outputs as well in the intermediate process to give the desired output that you require. So yeah, I hope with this we completed asynchronous counters. So I hope this is fine. Uh, is it fine, guys? Okay. Yeah. Okay. We are moving on to parallel counters. Okay. Yeah. I mean, this is. I mean, the name suggests. I mean, as the name suggests, it's we have a common clock pulse, which makes sure uh, the process you do is consistent across the entire counter, across the flip flops. I mean, and the process you do occurs at the same time toward the counter. Okay, so the flip flops are clocked at the same time by a common clock pulse. So yeah, except that there's nothing much to explain in this. I mean, all the stuff which I supposed to explain in this is explained in the asynchronous itself. So basically, what happens is, in ripple counters, you saw that the clock of the more significant flip flop uh, is dependent on the output of the previous. I mean, the less significant flip flop output, right? So that's why it's a ripple. It depends on each other. It depends on the one before it. And that's why it's called that was called ripple counters. Here there's no such case. Okay, everything is connected to common clock, so everything occurs at the same time. Okay, so that's why it's called parallel counters as well. Okay, so yeah, this is a 2-bit synchronous binary counter uh, using identical T flip flops or JK flip flops, identical JK inputs. The same inputs and outputs you can make in parallel counters. So you just have the same clock. So instead of that, what you do is you play with the G and K. I mean, you play with the inputs of actual inputs of the flip flops. Okay, instead of playing with the, I mean, instead of connecting the output of the less significant flip flop with the higher clock of the higher significant flip flop, you connect the output of the less significant flip flop to the inputs, other inputs of the more significant flip flop. Okay, so this is a way to work around this. Okay, so yeah, we come to the place where we first require some. This is a very important part. Designing a synchronous counter. Uh, yeah. So just give me 1 second. Give me 1 second. I will come back. Okay, guys. So let's move on to where is it? Yeah. Let's move on to designing a synchronous counter. Okay. So, I mean, before studying the design of counters, it is important to understand three tables. Okay. Uh, Truth table, characteristic table, and excitation table. Uh, these tables are very important, uh, and you need to memorize them. Okay, to make your life easier. Okay, so I will explain in clearer manner. Okay, so first, truth table. Uh, in truth table, I mean, see, in these tables there is a particular pattern which goes on, right? So you have an input, and based on that input, uh, the output will be mentioned. I mean, the output will be determined, right? So when it comes to truth table, depending on clock and the input value is j and k, the next state, I mean, the output of the next state is determined. Okay. So, for example, if the clock is down, irrespective of the uh, states of, I mean, irrespective of the inputs of J and K, it's going to change, stay the same. I mean, stay the same. Okay. So we saw this earlier. Okay. So I think truth table is pretty easy. Okay. So let's move on to characteristic table. So characteristic table sort of like an Excel sheet. Okay. Let's take this analogy. Let's say you are working on an Excel sheet. And J is analogous to rows of the Excel sheet, and K is analogous to columns. Okay, so when the let's say it's an already like it's not a new Excel sheet. There's something on already on it. Okay, so when Q of n is the current state. Current state. Okay, so what to say? Let's say you create a new Excel sheet, and then you have nothing involved. You have no rows and no columns in it. So obviously, the next time you open it will also be. Let's assume that. I mean, Excel doesn't let you save blank files technically, but let's assume does. Okay. So you open an Excel sheet, you do nothing on it, and you save it. That's how this first table will look. That's this first part will look like. Let's say you open a sheet and you pin reset. What does reset do? It changes everything back to zero. Again, there'll be no change. Then you do set. And so what happens? The next state, there'll be some info on it. And then the next subsequently, when you have both J and K are both on it, are both set to I, and then you save it. What happens is it now there'll be something on it the next time you open the file, right? So Q1 is one, the current state is one, and depending on that, the next stage will subsequently change. Okay. Okay, I shouldn't have said it J and K as wrong concept. Let's consider J and K as undo redo. Okay, I think that would be a better analogy. Okay, so uh, when there's nothing on a file, what is the process of undoing it? I mean, what's the use of undoing stuff? It doesn't matter. There's nothing to undo. There's nothing to redo. So it remains in zero. So yeah, I think you get the analogy. I mean, when there's something saved, but you do no change to it, it remains in the same state. When you undo something, it gets undooed. When you redo something, you get redo. It gets redo. And then when you do both undo and redo at the same time, nothing can happen. It goes to the toggle state. Okay. I mean, it already went to the toggle state. Sorry. Yeah. Okay. It went to the toggle state. Okay. So it gets repeatedly switched between undo and redo eternally. Okay. So this is what characteristic table is. So characteristic table, it shows what the current state is. It shows what the input you give. It shows the inputs that you give, and it will show the next state of the table, right? So that's that. Next is excitation table. This is where it gets somewhat tricky. Okay. So excitation table, you have the current state, you will have the next state. Based on that, you have to determine the values of J and K which could have led to that result. Okay. So For example, let's take in the JK flip flop, set and this is set and this is reset, right? So when in order uh, for the in order to let the flip flop be the same state and to have no changes, that is both Q and Q1 plus one should be in stable state. For that to happen, uh, it is enough to have J at zero, irrespective of K, because what K is one, right? So anyways, it's gonna put it back to zero. So I mean, see, sorry, K is reset, right? So irrespective of the value of K, if J is zero, it's gonna remain zero. Okay. And then when it's zero, I mean, when there's some change, I mean, it gets incremented by the next stage. This uh, obvious that the J should be involved. The set value should be activated, and irrespective of the value of K, it's going to be one. And then when it's 1 0, the same stuff occurs. Okay, so by the way, this is how I mean this is how excitation table works, and this excitation table is very important when it comes to making I mean designing the synchronous circuits. I mean synchronous counters. Okay, this is very important, and you need to remember this excitation table for all of the flip flops. Okay, which are given. I mean, the thing is, you can figure out the concept, but it's time consuming. You can't go the exam and just make out the concept and during that time, right? And this is pretty complex concept also. Okay. So like see, I mean, there's a very less chance that you can figure out, okay, this is set pin, this is a reset pin. So zero, if the only J is zero, K need not be anything. I mean, those concepts, this may be clear to but there's no guarantee that you can have the same uh, clarity during exam, all right. So because of that, it is preferred to memorize these tables. Sorry, excitation table is very important to design a circuit. So make sure you have that have them in mind, and importantly make sure you don't confuse between the excitation tables of different flip flops. Okay, that will because if you mess up the excitation table, the entire design of your counter will go wrong. Okay, so that's what it is. And yeah, there's nothing to explain here. You need to memorize this. It's preferred to memorize excitation table for everything. Okay, but for SR flip flop, basically for SR flip flops, I mean here we have don't care, we have zero, because obviously when in JK flip flops and both are one, you have this particular cushion called toggle state. In SR there's no such state. So basically, there's no place where uh, Qn is zero and Qn plus one is zero, and you can't just say irrespective of R, I can have S as one. That is no, you can't say that. S has to be one and R has to be zero for this particular change to occur. For Qn to be zero and Qn plus one to be one, only this configuration is possible. So that's why you have here zero. Okay, so this is how actual mechanism works. But again, it's preferred to memorize all of them. And this is for T, uh, T 0 0 0, and this is pretty simple. Only since only one input is involved, it changes accordingly. Okay, so this is how flip flops that the three tables work. Um, so I hope where is the message? Okay, so is it clear, guys? 1 second. Yeah, we'll continue. So, yeah, we have come to the most important topic, according to my opinion, in this chapter. Okay, so um, listen to this with bit of a caution. Okay, so this is the design of the designing the synchronous counters. Um, this is a process for designing the synchronous counters. Okay, so you basically have these following steps. Okay, so first of all, this is pretty easy. You identify the number of flip flops and the type of flip flop which is required. How do you decide? It's very easy. They will just give it in a question. Okay. Uh, you decide it and you just identify the number of flip flops required and the type of flip flop required as well. And what you do is you put the excitation table of the flip flop. Okay. So that's what you saw here. Okay. Based on the flip flop they gave, you have to write down the flip flops corresponding excitation table down. Okay. And then based on the excitation table of each flip flop, you draw the state diagram and you draw the excitation table of the whole circuit. Makes sense. You have various flip flops, right? So write down the, I mean, you draw the excitation table, uh, integrating all the flip flops in it. Okay, and then using the excitation table, you deduce the uh, equations using K maps. Okay, and then in the K maps you get the equations, and based on that you can draw the logic diagram. Okay, so I could draw, but I could explain it. I mean, we have these practice examples. So, I mean, I was planning on writing down and explaining you, but since it's very late, I have templates for it. So I'll just explain you via this. Okay, let's start with this. So 2-bit synchronous counters by JK flip flop. Okay, so wait a minute. Oh my God. Yeah. Okay. Yeah. So we have two bits synchronous counters by JK flip flop. Okay. So as I said before, first step is you have to identify the number of flip flops and the type of flip flop required as well. So here it's 2 bits, so obviously two flip flops, and then the type is JK flip flop, obviously. And then you draw the excitation table of the flip flop which is given, which is asked. So since here it's JK flip flop, you draw the excitation table of JK flip flop, and then what you do is you draw the state diagram, and the state diagram is pretty easy. You just since obviously two bit now, what will go? It will go to 0, 1, 2, and 3, and it will come back uh, down to 0. Right? So that's what you mentioned here. Uh, and then this state table for the entire circuit. I mean, so what you do is you take the so you say see you here you have okay, this is Qn and this is Qn star. Okay, I mean sorry, yeah, Qn star. Okay, so what you do is you take that flip flop. Uh, let's say Q1. Okay, since it's the most significant digit here, you would take Q1, the current state. You note down the values. You would take the other flip flop's current state and you note down the uh, various possible configurations. And then what you do is you go to the state diagram. Let's say for 0 0. Okay, so for 0 0, you look at the next possible state for that. Okay, so in this case, if q1 is 0 and q0 is 0, the next state is obviously 0 1, right? So you write that here, and for this you write here, right? So what you do now is you look at the let's and then you write down the J1 K1 and I mean J1 K1 and J0 K0. Okay. So obviously for each flip flop you do the same J and K values. So now what you do is for J1 you look at the values of q1 and q1 star. Okay. So for possible values of 0 and 0, I mean, you look at this table, and for the values which are here, you have to find look up to this table and find out what could be the values for j and k. Okay, in this case, since it's 0 0, you look at this table where we will get 0 0. 0 0 is possible when j is 0 and k is don't care. So write it here. Okay, and then for this 0 and 1, you get 1 and don't care. For 1 and 1, you get don't care and 0. So subsequently, you write that for J1 K1. And for J0 K0, you follow the same procedure. 0 and 1. What is a possible, I mean, for what configuration of J and K will you get 0 and 1? 1 and don't care. And then for here, for don't care and 1. 1 and don't care and 1. So you write this down. Okay. So this is the most important one. Make sure you don't do any mistake. Double check this table twice, thrice to ensure you don't do any mistake. Uh, So yeah, this is the most important step in this designing process. Okay. So next step is finding Boolean expression. Okay. So what you do is you take each of the flip flop. I mean, you take each input of the flip flop and then you put a k map around it. For J1, you look at the Q1 and Q0, and then you put out the following values for it. What do you find for it? For in case of J1, it's Q1 and Q0. So like what is it? For J1 to be 0, you find out how what it's gonna be 0 0 for Q1 and Q0. So like you get what I'm trying to say, right? For the each flip flop, you find out the values of Q1 and Q0, and then you put a K map around it, and the value of that K map will be equal to the input j r k. Okay, so after you do that, you will get this. Um, you get this. So j1 will be q naught, and k1 will be q naught, and I mean j0 will be I, and j0 means j0 will be 1 and k0 will be 1. Okay, so I think making k map is pretty, I mean, they would have explained you about making k maps, right? So yeah, using that you just find out this, and using this equations you make the circuit. Okay, you first write, I mean, you first draw down the flip flops which you need to do. Since you have two flip flops, you just draw them. Then connect the dots, obviously. So J1 is connected to Q0. So so you do this. Uh, I mean, by the way, the leftmost, I mean, the most significant one will be connected to, I mean, wait, most significant, I don't know. Okay, see, basically, the least significant one is connected to 1. Okay, is grounded to 1. And you connect a common, don't forget to, never forget to draw this common clock signal. Okay, I'm talking from experience. Please don't forget. Okay, so you tend to easily remember it and you get the fruits of your misadventure later. Okay, so please don't forget. Okay, so these are stable. This and this is we have to draw, and rest of the stuff is depending on the equation. Okay, J1 is connected to Q0, so you connect this, and K1 is connected to Q0, so again you connect to this. J1 is connected. J0 is connected to 1, so you do this. K0 is connected to 1, so you do this. Okay, and then you output the q naught and q1, obviously. Okay, so this is how you design a n bit synchronous up counter or down counter. Okay, for down counter the process is same, only thing is the state diagram will be changes. So obviously subsequently there will be changes in this table as well, but the concept is same for both. Okay, so this is just another example for 3-bit using T flip flop. See, the steps are same. You see, the steps are pretty much same. Like you find out the number of bits, you find out the type of flip flop required, and so you find a number of flip flop required, and you find the type of flip flop required, and you write the excitation table for the flip flop, and then you draw the state diagram for it. I'm sorry, this is not a down counter. This is a normal up counter. Okay, but yeah. You draw the state diagram for it, and then you do the same. You write Q2, you write this values here, and you write what could be the next values of that. And then depending on that, you figure out the values of T2, T1, and T0. It's just look up the table and write down. So what that means is you have to memorize this to make your life easier on the exam hall. Okay, memorize the excitation table for the all flip flops possible. Okay, so yeah, then using that you find the Boolean expression. Okay, and then using the Boolean expression you design the counter. Okay, so this is how you mess around with the counters. Yeah, guys. So before moving on, is there any doubts? I hope is it clear? If it's clear, kindly react. Okay, wonderful. Um, yeah. Okay, guys. So with this, the most important parts of, the most tedious parts of our chapter are over. Uh, and then just a heads up, guys. Uday just informed me. He told that he will be taking Unit 5 tomorrow. Okay, so he'll be since obviously it's already 10:40 right now, so you'll be taking the unit 5 tomorrow. Okay, and the timings will be sent out in common groups. Okay, so yeah, next we move on to what registers. Okay, this is a very easy topic. i mean I mean I get the fact that the diagrams look very bad at first glance, but like the concept is very simple. Okay. So what are registers? What does the word register mean? It's register means store. That's what it does. It is a group of storage elements which is read or written as a unit. It's basically a bunch of stuff which does the same stuff for stuff which is storage. Okay. So as usual, this works based on flip flops. Okay. And then these are collection of flip flops with common control. That's fine. Okay. So next examples of register is storage registers and shift registers. Okay. So this is a pretty important distinction to make. Okay. So what is storage registers? So these are basic storage registers which uses flip flops. That's self-explanatory. So what you do is, uh, let's say I have a 4-bit storage register here. Okay. So each bit of an input will have its own flip flop to store its info. Okay. For example, you have this IN1 here. This IN1 has its own flip flop. Not exactly, but you get what I mean, right? It has its own place to store its info. Okay. So as long as it's a D flip flop, by the way. This is set and reset is for this. It means set and reset here. Okay. Don't get confused. It's a D flip flop. Okay. So D and Q. Based on year, as long as there's no change year and year, it stores the info, there's no change, and then it outputs. Sorry, wait, yeah, it outputs. Okay, and then when there's subsequently when there's a change in the when set pin or reset pin is activated, you get the changes. Okay, okay, wait a minute. Picture mode. Yeah, yeah. So same for IN2, same for IN3 and IN4. Okay. Basically, each bit has its own storage register. Okay. So that's what it is. And then next, shift register. So what does shift register does? So shift register holds successively sampled input values. So what it does is it has one single line for input. Okay. So this works sort of like a stack. Not stack. Okay, fine. Your first year is right. Okay, so you won't get confused between stack. So it's just how stack works, right? You put in one info, it says at one point, and then you stack something on top of it. The one which you gave in earlier will go down, right? So that's what happens here. When you give the first input, it stays here. Again, when you give the second input, the first input goes from year to year. Wait, sorry. Yeah. When you give the first input, it stays here. And then when you give the second input, this goes here, and then new input stays here. And then subsequently, this goes here, and this goes here, this goes here. So yeah, this is what happening. This is what happens in a shift register. Okay. So you the advantage of this is you have a single input. It's a serial input. Yeah. I mean, you will see the type of registers, but here the advantage is you can move with just a single, like, shift register provides you with the option of choosing between serial input and parallel input. Okay, storage doesn't. Okay, it has to be parallel input. So shift, that's the advantage of shift registers. So yeah, um, yeah, some of the applications of shift registers is to do the parallel to serial conversion for signal transmission. So yeah, basically, it takes the parallel inputs and does the same stack like operation and will connect it to serial stuff. Okay, so that's what happens. And then yeah, pattern recognition also does. Okay, yeah, that's what it is. So next, serial. I mean, sorry, shift registers type. There are four types of shift registers. Okay, so serial in, serial out, serial in, parallel in, serial out, and parallel in, serial. I mean, parallel in, parallel out. Okay, so these are the four types of main types of serial shift. Main types of shift registers. Um, so first, serial in, serial out. I mean, it's very simple. You have a serial input. You have a serial input. The output of the first flip flop is given as the input of the second flip flop, and subsequently, this is what happens. Okay, so yeah, you don't necessarily extract outputs here and all. So this doesn't happen. So you just have a single point for getting output, and you have a single point for getting inputs. And then I mean, the inputs and outputs are taken subsequently in a serialized manner. And that's what serial in and serial out shift register is about. Next, serial in parallel. So what it does is it has the same serial input. It just has one input string. But what it does is it extracts outputs from at each point of flip flop. I mean, at each flip flop. Okay. So that it gets info at every point. Okay. So the rest of the stuff is same. And then next is parallel in, serial out. Um, yeah. One second. One second. Yeah. Parallel in, serial out. Okay. Next. Yeah, it's pretty simple. You just have a shift register. I mean, you have a shift path, and then you have all these parallel inputs here. And the shift is connected to uh, what is it? You have both yes and no here. Okay, so what it does is you have this AND input here. So depending on what you want, either you can take in the parallel input, or it can take in the value from the previous flip flop. Okay, so it chooses and it uses and to signal out. If this is zero, this gets eliminated. If this if this is selected, I mean, if this is selected, this I mean this if this is sorry, this is selected, this gets zero. So obviously this entire stream stuff will cut off, and so vice versa. Okay, and then out of these two, one is chosen, and then anyways, basically what it means is you will get an input no matter what. Okay, uh, and then uh, you have a single output source. I mean, you have a single way of to get your output. Okay, so that's why it's parallel in and serial out. Yeah. and then next is parallel in parallel, and this is pretty simple. You get, for each flip flop you get an uh, input and you get an output. The only thing which connects everything together is a common clock uh, waves and the clear pattern. Okay, so that is that. And then bidirectional shift register. So what you have is, here is you have provisions for both left shift. You have provisions for both left shift as well as right shift. Okay, so what it does is, I mean, yeah, when right is selected, uh, yeah, see, I mean, the diagram might sound, I mean, diagram is complex, but there's nothing to explain here. Okay, so when right is selected, you get input from here. The input here is selected, so it goes here, and then it goes here, it goes here, it goes here, goes here, and then output is given. Okay, I mean, sorry, that's for left shift. Sorry, and then if right shift is selected, the input goes from here. It goes from, I'm sorry, it goes from it what? Yeah, it goes from, I'm sorry. So this input, you see this input right here. Uh, you see this input here. So it goes here, it goes here, and then wait, what? I don't know. I mean, see, wait. See, basically what I mean to say is there is a provision for the register to move both left and right. Okay, so that's what this bidirectional shifted register is about. So, if at all they ask you to draw this stuff, I don't think so. There's highly unlikely, but just to be sure, what you do is, okay. So what you do is, you just make sure. Oh my God, wait a minute, wait a minute. Yeah, wrong. Incorrect. 1 second, please. 1 second. Yes, yeah. So where was I? Yeah. So basically, what you need to draw is you have to have an you ought to have an right or left shift decider here. I don't know how to mention it. Let's just term it as decider. So based on this, you need to connect it with and pin of everything, and then you have this input here. You need to connect this one end should be connected to. I mean, one input should be connected here, and the same input should be connected at the right end also. Okay, and then rest is just the same. You have the both of them connected on, I mean, if in both of them, if one is connected in one pin and gate, the other should be connected to the other AND gate, and then you connect all of them, and you connect both of these AND gates for everything with the OR gate, and then you give it the input here in D, and then you give the output as the input of the second one here, and it goes on like this. And then also you provide provision to even go this way. It goes here. Okay, here. Oh wait, what? Oh, the screen is not shared. Sorry, sorry. Where is it? Share. Sorry, sorry. Is this visible now? Okay, yeah, sorry, I didn't notice. Sorry. So yeah, oh my God, wait. Okay, I mean, see, basically, what I was saying was, uh, you just uh, draw this first. This is I mean, let's term this as uh, shift direction decider. Okay, so basically, I have a NOT gate here, and then you connect these. Okay, you first draw that, and then what you do is you connect. You have the input, side of input. I mean, it should be connected. The input should be connected on both the sides. That's how you. I mean, God. Yeah. So it should be connected to both sides. Then what you do is, if for you ought to have many AND gates, right? In this case, you have 2, 4, 6, 8. So basically, you have two AND gates for each flip flop. Okay. If one AND gate in that for each flip flop is one AND gate is connected to one side of this, another AND gate should be connected to the other side. Okay. So do this for every AND gate you find, and then in the leftmost input, you start here and then you draw this. You have an OR gate to connect both the AND gates. You go through D and you find an output Q. And what you do is you take this here, okay, and then you do the same process. You do it here, it goes through here, you do it here, and then what you do is the output comes here for left shift. Okay, so what happens now is uh, since you gave since you're also giving an right shift provision, you can make this here. Okay, do this thing here. I mean, sorry, wait, what? It's not getting. So basically, what I was trying to say is uh, the output of Q is connected to the. I mean, see, the cabling here is pretty complex, but yeah, the output here is given here. Okay, so the stuff happens, and then it goes here, and this comes here, and then this happens, and then this comes here, and then this goes here. Okay, so you see how this works, right? So this is how you need to draw the bidirectional shift register. There's nothing to explain here. This is just a way to remember how to draw this register so that you don't miss out anything. Okay. Again, very important point. Please don't forget to draw the clock here. If you don't draw this clock here, I mean clock lines here, it is not a counter. I mean, sorry, it is not a register at all. Okay, so please, that is one thing. And then universal shift register. So it is basically bidirectional shift register along with parallel load capacities. So basically, you add an extra multiplexer for every flip flop in the bidirectional shift register, and this is a universal shift register. So what are the connections in the multiplexer here? Okay. So the first input, uh, that is zeroth pin of the multiplexer, is connected to the output of the corresponding flip flop. I see. Where is it? Where is so yeah, this you see, this is connected to the output of the flip flop, and zero is connected to the output of the flip flop. You see, zeroth pin is connected to the output of the flip flop. Okay. The first pin of the multiplexer. Keep this in mind. First pin of the multiplexer, uh, is connected to the output of the very previous flip flop. Okay, so this one pin, first pin will facilitate the right shift for you. Okay, and then the second pin of the multiplexer is for the left shift. Obviously, it's connected to the output of the very next flip flop. Okay, so it can facilitates left shift. And the fourth pin is for parallel loading capacities. So basically, it's connected to individual bits of inputs. Okay, so see, you have everything. It's basically connected everywhere. Okay, yeah. So this is what is the operations of the universal shift registers, and this is what multiplexers work with. And then so universal shift registers is done. And then with that, you have the applications of that. uh, Advantages, obviously, we have the advantages here. This register can perform three operations such as left shift, right shift, and parallel loading. It can perform serial to parallel. It has all provisions. Okay. uh, you can perform input, I mean, same, yeah. This register acts as the interface between one device to another device to transfer the data. Since this has everything in it, you can use it. You can use this anywhere. Okay. So application is, it is used in microcontrollers for input output expansion. It is also used as a memory element in computers. And then, I mean, there's this thing. It's used in time delay applications, and it is used as frequency counters, and it uses binary counters, and it is used as digital clocks. Okay. So with that, we complete our chapter, right? So, wonderful. So unit 4 is done. Uh, I hope I hope you guys are fine with this. Uh, is there any doubts for you, or is everything clear? Everything's clear, right? Okay, wonderful. So, yeah, guys, as I mentioned before, they will be taking Unit 5 tomorrow, and will be mentioning the time on the message. Uh, so, yeah, almost எவ்வளோ நான் எடுத்தேன் நான் 8:45. I started at 8:45, right? So, damn, 8:45 by 10:45. Almost 2 hours 15 minutes. Okay. So, it required this time for to be properly taught. Okay. So, yeah. I hope you guys understood the concepts that I taught, and yeah, keep visiting our YouTube channel for more such tutorials. And yeah, guys, thank you for staying. Thank you, and yeah, guys, you can leave the meet. Yeah, bye, bye, bye.